The observable universe is the vast expanse that we, from our vantage point on Earth, can observe in principle. However, this represents only a fraction of the entire universe, which is believed to extend far beyond what we can currently detect. This observable region spans across the cosmos, defined by the light that has had enough time to reach us since the beginning of cosmic time. It's like a window into the grand unfolding of cosmic history, where we catch glimpses of galaxies, stars, planets, and myriad astronomical phenomena, each contributing to the intricate narrative of the universe's past and its dynamic nature. At the heart of our understanding lies the age of the universe, estimated to be around 13.8 billion years old. This is not just a number. It's a testament to the unimaginable scope of time and the ever-changing nature of the cosmos. Determining this age isn't a simple task. It involves a combination of observational data and theoretical models. A crucial piece of this cosmic puzzle is the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation, which dates back to a time when the universe was just 380,000 years old, acts as a snapshot of the infant universe. By studying its properties, scientists can peer back in time to estimate the age of the cosmos. Beyond the cosmic microwave background, other key indicators provide further clues. For instance, the age of the oldest stars in the universe gives us a sense of the passage of time, while the rate at which the universe is expanding, known as the Hubble constant, offers vital information about the universe's evolution. By measuring the distance to galaxies and observing their velocity as they recede from us, astronomers can piece together how long it's taken for the universe to reach its current state. Each discovery builds a compelling picture of a universe that began in a moment of incredible energy and expansion, continuing to unfold over billions of years, with mysteries still waiting to be unraveled. Yet, as we explore the immense universe, there is another, equally expansive universe that many of us navigate daily, the digital one. Unlike the physical cosmos, our online universe can often feel like a vast and ever-encroaching black hole, especially when it comes to personal privacy. It's unsettling, for instance, when private information, things like your full name, email, or even home address, is exposed and traded across countless platforms, accessible to anyone who knows where to look. I personally searched my own name online and was shocked to find my details spread across multiple data broker sites. The discovery was both surprising and deeply unsettling. What's even more alarming is the fact that companies we trust can sometimes be the ones putting our information at risk. For instance, AT&T recently revealed that over 73 million customer records, spanning both current and former customers, had been released onto the dark web. The company recommended that those affected take steps like using stronger passwords, monitoring account activity, and considering credit freezes or fraud alerts. But what if you don't want to handle all that yourself? That's where Aura, the sponsor of today's video, comes in. Aura takes the hassle out of protecting your personal information by combining multiple features into a single, easy-to-use service. Unlike downloading several apps to secure your data, Aura provides a comprehensive approach to safeguard your privacy. They use cutting-edge technology, much like the advanced tech we use to protect our astronomical observatories, ensuring your personal universe is just as secure as the real one. I believe in taking every possible step to protect my personal information, just as we take great care to protect our understanding of the night sky. By using Aura, you're locking all potential points of entry, ensuring your digital space is safe and secure. You can start a 2-week free trial by visiting aura.com/spacedust and discover how you can protect your digital universe from harm. Now, let's shift back to the physical universe. At the most fundamental level, 4 essential forces of nature shape everything we observe. These forces, the force of gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, act as the unseen architects of our reality. Gravity, the most familiar of these forces, is the attraction between objects that have mass or energy. It's what holds planets in orbit around stars and allows galaxies to form. Electromagnetism governs the interactions between charged particles, helping to bind electrons to atomic nuclei, setting the stage for chemistry and, ultimately, life as we know it. The weak nuclear force, while less familiar, is just as vital. It's responsible for radioactive decay and certain nuclear reactions, including those that fuel the sun. The strong nuclear force, on the other hand, is the mightiest of them all. It binds quarks together to form protons and neutrons, and it holds the nucleus of atoms together, overcoming the repulsive forces between positively charged protons. These four forces, distinct yet interconnected, are the very building blocks of our universe, shaping the world around us and driving the phenomena we witness every day. Then there's dark matter, an elusive and mysterious substance that constitutes a significant portion of the universe. While dark matter cannot be seen with traditional telescopes since it doesn't emit, absorb, or reflect light, its presence is inferred from its gravitational effects on visible matter. This invisible matter accounts for roughly 85% of the total mass of the universe, though we cannot directly observe it. One example of dark matter's influence can be seen in the rotation speeds of galaxies. Without an invisible mass, galaxies would spin so rapidly that they would tear themselves apart. Additionally, dark matter plays a crucial role in the phenomenon known as gravitational lensing, where the light from distant galaxies bends as it passes through a foreground galaxy. This bending of light suggests that there is far more mass in the universe than meets the eye. Dark matter is not just a passive presence. It acts as the scaffolding that supports the formation of galaxies and clusters of galaxies, playing a critical role in shaping the cosmos. Without it, the universe as we know it would be vastly different, and many of the structures we observe would not have formed. It's this invisible force that continues to shape the universe, leaving scientists with an enduring mystery to explore, a mystery that continues to intrigue and challenge our understanding of the cosmos. But amidst the awe-inspiring vastness of the universe, there exists a profoundly mysterious component of the cosmic puzzle: dark energy. This enigmatic force, which permeates the very fabric of space, plays a pivotal role in the expansion of the cosmos. Unlike gravity, which pulls objects toward one another, dark energy exerts a repulsive force, causing the universe to expand at an accelerating rate. Its discovery in the late 1990s revolutionized our understanding of the cosmos. Astronomers, while studying distant supernovae, observed that these exploding stars were further away than theoretical models had predicted. This unexpected result pointed to a startling truth: the universe's expansion wasn't slowing down as once assumed, but was speeding up. Dark energy constitutes a staggering 68% of the total energy content of the universe, vastly overshadowing both dark matter and ordinary matter. Its true nature, however, remains one of the greatest mysteries in modern cosmology. Despite this, its effects are undeniable. By driving the accelerated expansion of the universe, dark energy shapes the fate of all cosmic structures. It is the invisible hand that determines how galaxies, stars, and other celestial objects will evolve over time. This presence challenges our understanding of physics, pushing us to explore profound questions about the origin, composition, and ultimate destiny of the universe. In a sense, the mystery of dark energy is the key to unlocking the universe's most fundamental secrets. The cosmic microwave background radiation, CMB, is another monumental discovery that provides a window into the infant universe. This faint afterglow of the Big Bang fills the entire cosmos, offering a snapshot of the universe at a time approximately 380,000 years after the Big Bang, when the cosmos cooled enough for protons and electrons to combine into neutral atoms. This event allowed light to travel freely for the first time. Predicted by theorists in the mid-20th century, the CMB was accidentally discovered in 1965 by Arno Penzias and Robert Wilson, a discovery that earned them the Nobel Prize in Physics. The CMB is astonishingly uniform, with temperature variations of only 1 part in 100,000. Yet within these subtle fluctuations lies an invaluable trove of information about the early universe, its composition, its age, and the very process by which cosmic structures formed. Through studying the CMB, scientists are able to piece together the history and evolution of the universe with unprecedented clarity. Black holes, those enigmatic regions of spacetime where gravity's pull is so intense that not even light can escape, form from the remnants of massive stars. When a star exhausts its nuclear fuel, it collapses under its own gravity, leading to a cataclysmic supernova explosion. If the remaining core is more than about 3 times the mass of the Sun, it will collapse into a black hole. There are 3 primary types of black holes: stellar mass black holes, which are up to 20 times more massive than the Sun; supermassive black holes, which can be millions to billions of times more massive than the Sun and lie at the centers of galaxies, including our own Milky Way; and intermediate mass black holes, which bridge the gap between stellar mass and supermassive black holes. Each type plays a distinct role in the cosmos, influencing the evolution of galaxies and stars, and possibly even shaping the structure of the universe itself through their immense gravitational pull. Supermassive black holes, once thought to be rare anomalies, are now believed to exist at the heart of nearly every large galaxy, including our own. These colossal cosmic objects are not just passive entities. They actively shape the formation and evolution of galaxies, acting as the architects of the universe. A remarkable observation that underscores this relationship is the tight correlation between the mass of a supermassive black hole and the velocity dispersion of stars in the bulge of its host galaxy. This suggests a symbiotic connection that influences both the growth of the black hole and the galaxy itself. The mechanism behind this relationship likely involves active galactic nuclei, AGN, phases in which supermassive black holes actively accrete material. During this process, vast amounts of energy are released in the form of radiation and powerful jets, which can heat and disperse surrounding gas, regulating star formation within the galaxy. This feedback mechanism is crucial for explaining why the universe does not contain as many large galaxies as expected, were star formation left unchecked. In this cosmic ballet, supermassive black holes act as both anchors and sculptors of galaxies, guiding their growth and shaping their properties over billions of years. Wormholes, long cherished by science fiction enthusiasts, are theoretical passages through space-time that could provide shortcuts across the vast distances of the universe. Envisioned by Einstein's theory of general relativity, wormholes are solutions to the equations describing gravity, suggesting that the fabric of space-time could be bent and connected, forming a tunnel-like structure between 2 distant points in the cosmos. If such structures exist, they could allow for instantaneous travel between these points, bypassing the constraints of the speed of light. However, despite their tantalizing potential, wormholes remain purely theoretical. Even if they exist, numerous challenges would need to be overcome to make them traversable. One primary concern is stability. Theoretical models suggest that wormholes would collapse instantly without the presence of exotic matter, which would exert negative pressure or anti-gravity. Furthermore, navigating a wormhole would likely require energy and technology far beyond anything currently available. While wormholes remain firmly in the realm of theoretical physics, they continue to inspire both scientific research and popular imagination, awaiting further study and the possibility of empirical evidence. Gravitational waves, ripples in the fabric of space-time, travel at the speed of light and are generated by some of the most violent and energetic processes in the universe, such as merging black holes or neutron stars, or even the aftershocks of the Big Bang itself. These waves carry critical information about their origins and about the very nature of gravity that cannot be obtained through traditional astronomical tools. Einstein's theory of general relativity predicted the existence of gravitational waves back in 1916, suggesting that the acceleration of massive objects distorts space-time, creating waves that propagate outward. The first direct detection of gravitational waves, made by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, confirmed Einstein's century-old prediction, marking a monumental moment in both physics and astronomy. This breakthrough not only validated the existence of gravitational waves, but also opened up a new avenue for observing the cosmos, providing insights into some of the most extreme phenomena in the universe. In this exploration of the cosmos, these enigmatic forces and phenomena, dark energy, the cosmic microwave background, black holes, wormholes, and gravitational waves, represent the frontiers of human knowledge, revealing the universe's greatest mysteries and inviting us to delve deeper into the unknown. But also, the discovery of gravitational waves marked a monumental moment in astrophysics, providing the first concrete evidence of binary black hole mergers. This breakthrough has opened an entirely new window for observing the cosmos, enabling scientists to listen to the universe in a way never before possible. These ripples in space-time allow us to study events that are invisible or extremely difficult to observe with traditional telescopes. The ability to detect gravitational waves affirms Einstein's predictions from general relativity, revealing in a spectacular way how space-time is dynamic and malleable, reshaping our understanding of the universe. The shape of the universe, an enduring question that captivates cosmologists, remains one of the most profound and unresolved puzzles in modern astrophysics. According to general relativity, and with backing from the cosmic microwave background radiation, the universe is thought to take one of three possible shapes: flat, spherical, or hyperbolic. Each of these shapes suggests vastly different futures for the universe and its eventual fate. Recent measurements, most notably from the Planck satellite, have narrowed this down to the conclusion that the universe is flat, with a mere 2% margin of error. In a flat universe, parallel lines never meet, and the geometry we learn in school applies even on cosmic scales. However, this flatness brings with it a fascinating twist. If the universe is indeed flat, it could extend infinitely in all directions, provided that it shares the same physical properties and laws everywhere. But there's an intriguing possibility that the universe could also be flat yet curved back on itself in a higher dimension, much like the surface of an enormous balloon. In this case, the universe would be finite yet unbounded, suggesting a paradoxical structure where you could travel forever without ever encountering an edge. Despite these groundbreaking observations, questions about the exact shape and nature of the universe continue to challenge us, intertwining with the mysteries of dark matter, dark energy, and the very fabric of space-time itself. The age-old question of whether the universe is finite or infinite hinges on these mysteries, each contributing to an ever-evolving understanding of space. If the universe is flat, as current data from the cosmic microwave background suggests, it could theoretically extend forever. Yet, flatness doesn't rule out the possibility of a higher dimensional curve that is imperceptible to us, creating a finite universe within an infinite space. On the other hand, if the universe is closed and curved like a sphere, it would be finite. This scenario would allow for a fascinating possibility, traveling in one direction long enough to eventually arrive back at the same point, much like circumnavigating the Earth. The universe's expanding nature, driven by the mysterious force of dark energy, only complicates this question further. As the universe continues to stretch out, we are left with more questions than answers, and the enigma of its infinite or finite nature remains a captivating subject of speculation. Beyond the observable universe lies an even deeper mystery, a realm untouched by light's journey since the birth of the cosmos. The observable universe, a sphere with a radius of about 46.5 billion light-years, encompasses all the galaxies, stars, and celestial phenomena whose light has had the time to reach us in the 13-point-alien years since the Big Bang. However, what lies beyond this boundary is anyone's guess. Some theories suggest that the universe continues far beyond what we can see, extending infinitely and filled with galaxies and structures that mirror those we observe. The concept of the multiverse, which posits the existence of multiple universes, each with different physical laws, is one such speculative theory. But without direct evidence, these ideas remain grounded in the realm of theoretical physics, offering tantalizing possibilities, yet lacking empirical confirmation. As scientists peer further into the cosmos, one thing is clear. The laws of physics, as we understand them, seem to be universal and consistent throughout the observable universe. This assumption is the cornerstone of modern astronomy and physics, allowing scientists to study distant galaxies and phenomena with the expectation that the same principles governing matter and energy here on Earth apply across the universe. From the behavior of galaxies to the faint afterglow of the Big Bang, the cosmic microwave background radiation supports this notion, confirming the uniformity of the universe. Yet, what happens beyond the reach of our instruments? Could different regions of spacetime possess their own distinct laws or physical constants? While speculative theories like the multiverse propose such variations, the evidence remains elusive. What we do know, however, is that within the observable universe, there is an astonishing consistency in the laws of physics, suggesting that the universe is governed by a deep, underlying harmony. This realization that the very fabric of reality may be interconnected and finely tuned underscores the awe-inspiring nature of the cosmos. In the grand narrative of the universe, the formation of the elements is a story that stretches over billions of years. In the immediate aftermath of the Big Bang, the universe was a seething mass of hot, dense particles, protons, neutrons, and electrons. As the universe expanded and cooled, these particles combined to form the first atoms, primarily hydrogen, the simplest and most abundant element. Helium and trace amounts of lithium followed in this primordial soup, setting the stage for the creation of stars, galaxies, and all the complex structures we observe today. This ongoing process of stellar formation and elemental creation continues to unfold as the cosmos evolves into the vast and intricate expanse that surrounds us. But this was just the beginning. The real magic unfolded within the very cores of stars, enormous nuclear furnaces where the building blocks of the universe were forged. Here, within these stellar reactors, the primordial elements from the beginning of time were transformed through an awe-inspiring process known as stellar nucleosynthesis. As stars lived and died, they acted as cosmic foundries, like fusing lighter elements like hydrogen and helium into heavier elements such as carbon, oxygen, and nitrogen, the very elements essential to life as we know it. Through these complex nuclear reactions, stars not only illuminated the night sky, but became the crucibles where the ingredients for life were created. In the dramatic finale of a star's life cycle, particularly for the more massive stars, an extraordinary event occurs. A supernova explosion, one of the most cataclysmic and energetic events in the universe, ensures that these elements are scattered far and wide across space. These violent outbursts send a cascade of matter, including the very building blocks of life, into the vast cosmic expanse. This stellar debris seeds the clouds of gas and dust that will eventually give birth to new stars, planets, and, ultimately, the life forms that will call these planets home. When we observe the periodic table of elements, we are not just gazing at an abstract list of chemicals. We are looking at the legacy of countless stars that have lived, exploded, and died across eons, leaving behind the foundational materials that make up the universe. Yet, this cosmic tale takes a curious twist when we turn our attention to one of the universe's most enigmatic phenomena, the Great Attractor. Located approximately 250 million light-years away in the Norma cluster, this gravitational anomaly is so mysterious that it has puzzled astronomers for decades. Despite its location being behind the zone of avoidance, a region filled with dust and stars from our own galaxy that obstruct our view, scientists have detected its presence by studying its profound gravitational effects. The Great Attractor is not just an invisible force pulling on distant stars, it is exerting a gravitational influence on entire galaxies, including our own Milky Way. This mysterious entity is so massive that it contains the mass of tens of thousands of Milky Ways, drawing not just our galaxy but countless others toward it. The Great Attractor's immense gravitational pull, though unseen, is as real as it is unfathomable, guiding galaxies on a journey across the vast reaches of intergalactic space. As each galaxy falls into its gravitational well, it moves inexorably toward the center of this cosmic force. This gravitational pull, like a cosmic orchestra, shapes the very dance of the universe, emphasizing the interconnectedness of all galactic structures. It serves as a reminder that even the farthest reaches of the universe are not isolated, but bound together by the invisible hand of gravity. At the same time, the universe is also home to some of its most elusive mysteries, one of which lies in the theoretical realm of cosmic strings. These are hypothetical one-dimensional cracks in the fabric of space-time, originating from the chaotic conditions following the Big Bang. While they remain unproven, the idea of cosmic strings stirs the imagination of scientists and cosmologists alike. These theoretical structures, predicted by some models of the early universe, stretch for lengths far greater than even galaxies, yet they are incredibly thin, nearly invisible. If they do exist, cosmic strings could serve as a bridge to the earliest moments of the universe, providing a direct link to the turbulent birth of space and time itself. Although cosmic strings remain elusive, their potential discovery would be monumental, offering an extraordinary glimpse into the conditions of the universe's infancy. It would mark a new chapter in our understanding of the cosmos, shedding light on the fundamental laws of physics and perhaps even unlocking secrets about dark matter and dark energy, forces that we have only begun to comprehend. The quest to find these cosmic relics is a pursuit that could forever alter our understanding of the universe's origins and the complex fabric of space-time itself. But even the search for cosmic strings would pale in comparison to the awe-inspiring phenomenon known as the inflationary epoch. Occurring a fraction of a second after the Big Bang, this period was marked by an extraordinary expansion of the universe. In the blink of an eye, literally faster than the speed of light, space itself began to expand exponentially, growing by a factor of at least 100 quadrillion times its original size. This period, lasting only a minuscule fraction of a second, set the stage for the universe as we know it today, smoothing out any initial irregularities and establishing the foundation for the large-scale structures we see across the cosmos. The inflationary epoch helped explain why the universe appears flat and homogeneous on large scales, making it one of the most important and transformative periods in cosmic history. It was a time when the very laws of physics, as described by both Isaac Newton and Albert Einstein, were tested in ways that we can only begin to imagine. In its brief and explosive expansion, the universe became the vast, intricate, and interconnected cosmos that we explore, study, and wonder about today. But also lays the groundwork for the grand architecture of the cosmos itself. These early irregularities in the universe's formation, seeds planted during the fleeting inflationary period, would later evolve into the galaxies and clusters of galaxies that we observe today. As the universe expanded, it cooled, allowing the raw energy from the intense period of inflation to be converted into particles. These particles eventually bonded, forming matter in the physical world, from stars to planets to everything in between. The inflationary epoch, despite its brief duration, was undeniably pivotal in the history of the universe. It set the stage for the creation of everything we recognize today, from the birth of stars to the formation of galaxies and ultimately the emergence of life. The universe's cooling is a fascinating concept, particularly when we consider the theoretical limit of absolute zero. This temperature, 0 Kelvin, -270 degrees Celsius or -459.67 degrees Fahrenheit, signifies a state of no heat or motion at all. While the idea of absolute zero is captivating, it remains highly improbable according to the laws of thermodynamics. Despite the universe continuing to expand and cool, absolute zero is a state that's never been achieved, even under the most controlled laboratory conditions. Over the 13.8 billion years since the Big Bang, the cosmic microwave background, CMB radiation, the afterglow of the event, has cooled to just 2.7 Kelvin, a testament to the vast cooling that has occurred. However, the reach of absolute zero is out of the question. The third law of thermodynamics states that an infinite amount of work would be required to reach absolute zero, which makes it practically unreachable. More importantly, the very presence of the cosmic microwave background radiation suggests that the universe is filled with a low level of energy, keeping it above absolute zero. This energy, though small, is essential in maintaining the universe's temperature above the theoretical minimum. As the universe continues its expansion, dark energy, a mysterious and poorly understood force, further accelerates this growth, complicating the potential for the universe to ever reach a state of absolute cold. The most probable end state for the universe, according to current understanding, is not one of absolute zero, but what is known as heat death. In this scenario, the universe would reach a state of maximum entropy, where energy is evenly distributed and no region is warmer or colder than any other. While temperatures would be exceedingly low, they would still remain above absolute zero. This far-flung future is shaped by the inexorable expansion of the universe and the forces, dark energy and cosmic radiation, that continually drive its growth. This cosmic journey seems destined to never cool to the absolute minimum, thanks to the persistent energy that exists within the universe, ensuring its slow but inevitable progression toward entropy. In the voids between galaxies, a different kind of wonder lies hidden. These massive regions, known as supervoids, stretch across hundreds of millions of light years and contain little to no galaxies. The Bodi's void, discovered in the 1980s, is one of the most famous examples, spanning about 250 million light years, with only a handful of galaxies scattered within it. Despite their emptiness, these voids are not mere empty spaces. They are integral components of the universe's large-scale structure, positioned between the vast filaments of the cosmic web that link galaxies and galaxy clusters together. Supervoids provide invaluable insights into the very structure of the universe. Their properties are intricately tied to two of cosmology's most intriguing phenomena: dark matter and dark energy. Dark matter, through its gravitational influence, is thought to play a critical role in shaping the large-scale structure of the universe, including the formation of these vast voids and the dense filaments that link them. Dark energy, the force accelerating the universe's expansion, affects how these voids evolve over time. By studying supervoids, astronomers gain critical information about the early universe, specifically the conditions that arose following the Big Bang. According to inflation theory, the rapid expansion of the universe in its early moments created fluctuations in density that would eventually give rise to large-scale structures like voids and filaments. The study of these voids, then, offers a glimpse into the universe's infancy and helps refine our understanding of the forces that shaped it. As we turn our focus to the life cycles of stars, we find that their formation begins in the cold, dense molecular clouds scattered across galaxies. These stellar nurseries, composed mostly of hydrogen with traces of helium and heavier elements, serve as the birthplace of new stars. The process begins when a section of a molecular cloud collapses under its own gravity. Various triggers, such as the shock waves from nearby supernovae, collisions between clouds, or the effects of dark matter, can cause this collapse. As the gas and dust compress, the core heats up, and the pressure from the accumulating heat pushes outward against gravity, creating a balance that leads to the ignition of nuclear fusion. At around 10 million degrees Celsius, hydrogen atoms begin to fuse into helium, releasing vast amounts of energy in the process. This energy provides the outward pressure that balances the gravitational pull, marking the birth of a new star. Once nuclear fusion begins, the star enters the main sequence phase of its life. Depending on its mass, the star will spend millions to billions of years fusing hydrogen into helium in its core. The mass of the star dictates its fate, with the smallest stars eventually becoming white dwarfs after exhausting their fuel. Larger stars, however, may end their lives in a spectacular supernova explosion, leaving behind remnants like neutron stars or even black holes. The life cycle of a star is not just a tale of burning gas, but a cosmic event that shapes the very fabric of the universe, producing the elements necessary for life and shaping the galaxies in which they reside. Through these processes, stars illuminate the night sky, but more importantly, they forge the elements that make up planets, including our own. The death of stars, too, contributes to the evolution of the cosmos, enriching the universe with the building blocks of new worlds and life, but also plays a pivotal role in the chemical evolution of the universe, forging the very elements that create planets and, ultimately, life itself. The life cycle of a star is not merely a process of light and energy, but an intricate and awe-inspiring sequence of events, intricately governed by the mass it is born with. In its most basic form, the creation of a star begins with the collapse of vast clouds of gas and dust. These molecular clouds, under the weight of their own gravity, slowly coalesce into a dense region called a protostar. This young stellar object continues to amass matter from its surroundings, increasing the pressure and temperature at its core until it reaches a critical threshold, igniting nuclear fusion for the first time. And just like that, a true star is born. During the majority of its existence, a star remains in what is known as the main sequence phase. In this stable period, stars primarily fuse hydrogen atoms into helium at their cores, producing the energy and light we see. The length of this phase can vary dramatically, dependent on the star's mass. Massive stars burning through their hydrogen fuel at a rapid pace may only live for a few million years, a brief flash in the cosmic timeline. On the other hand, stars of smaller mass, like our Sun, can remain in this phase for billions of years, continuing to shine in the night sky. But as a star exhausts the hydrogen in its core, its fate takes a drastic turn. Smaller stars like the Sun begin to swell up into red giants, expanding to many times their original size. During this phase, the star begins fusing helium into heavier elements like carbon and oxygen. This process is an essential step in the creation of the chemical building blocks that make up planets and life. In stark contrast, the most massive stars evolve into red supergiants, capable of fusing elements all the way up to iron. The iron, however, is the final product of fusion in a star's life cycle, and when a star can no longer fuse iron into heavier elements, it faces its inevitable end. The death of a star, however, is determined largely by its mass. Smaller stars, like our Sun, shed their outer layers over time, leaving behind a dense, hot core known as a white dwarf. This white dwarf will continue to cool for billions of years, becoming fainter and fainter, eventually fading away into the cold depths of space. But in the case of massive stars, their end is much more spectacular. These stars die in a cataclysmic explosion called a supernova. A supernova marks one of the universe's most violent and energetic events, capable of outshining an entire galaxy for a brief period. But this explosion doesn't just end the life of the star. It often leaves behind the remnants of a neutron star or even a black hole. These stellar explosions also play an essential role in enriching the universe. As a supernova releases vast amounts of energy, it also scatters heavier elements into the interstellar medium, elements that will later become part of new stars, planets, and potentially new forms of life. This cycle of stellar birth, death, and rebirth is a fundamental process of cosmic evolution, where each star's death is just the beginning of something new. In this way, stars are not only the creators of light and energy, but the very fabric of the universe's ongoing transformation. Now consider binary star systems. These systems, in which two stars are gravitationally bound and orbit a common center of mass, provide a unique and fascinating glimpse into the complex dynamics of stellar evolution. These stars interact in profound ways, and their mutual gravitational pull can have a significant impact on their life cycles. The effects are especially dramatic in close binary systems where the stars are in close proximity. One of the most extraordinary phenomena that occur in such systems is mass transfer. When one star in a binary system expands into a red giant, its outer layers may extend beyond a certain point, known as the Roche lobe. This happens when the star's outer layers enter the gravitational sphere of its companion star, which then accretes material from the donor star. This process can cause profound changes in the companion star's mass, luminosity, and even its evolutionary path. In some cases, the mass transfer from the donor star can strip it down to a bare core, rapidly accelerating its journey toward becoming a white dwarf. But these systems are even more complex. There are instances when a binary system goes through a common envelope phase, where one star envelopes the other, creating a shared outer atmosphere. This phase can lead to a dramatic reduction in the distance between the stars, and in some cases, the stars may eventually merge into a single, more massive object. These mergers can give rise to highly unusual stellar objects, or in the case of compact objects like neutron stars or black holes, produce powerful gravitational waves that are detectable by observatories on Earth. Moreover, the presence of a companion star can influence the outcome of a supernova explosion. In a close binary system, for example, where one star has become a white dwarf and is accreting matter from its companion, the added mass can trigger a thermonuclear explosion, leading to a type Ia supernova. This explosion can destroy the white dwarf and dramatically affect the evolution of its companion star. Such interactions offer a glimpse into the complex and dynamic nature of stellar life cycles, where the gravitational dance between two stars can give rise to phenomena that are as fascinating as they are unpredictable. Thus, the intricacies of binary star systems add a layer of complexity to our understanding of stellar evolution. These systems not only contribute to our knowledge of how stars live and die, but also offer insights into the more nuanced aspects of astrophysics, revealing the interconnectedness of all things in the cosmos. The life cycle of stars, and especially those within binary systems, provides us with a rich tapestry of stellar phenomena, showcasing the vast diversity and ongoing transformation of the universe itself. Supernovae are among the most awe-inspiring and destructive events in the universe, marking the cataclysmic end of a star's life cycle. These explosions are so immense that, for a brief moment, they can outshine entire galaxies, releasing more energy than the sun will emit in its entire lifetime. There are two primary types of supernovae, each resulting from different stellar processes, but both are fundamental to our understanding of the cosmos. The first type, known as a Type 1a supernova, occurs in a binary star system where one of the stars is a white dwarf. A white dwarf is the remnant of a star that has exhausted its nuclear fuel and no longer undergoes fusion. In a binary system, this white dwarf begins to accrete material from its companion star, which is often a red giant. As it pulls matter from the companion, the white dwarf's mass increases until it approaches a critical threshold, approximately 1.4 times the mass of the Sun, known as the Chandrasekhar limit. At this point, the gravitational pressure becomes so intense that it ignites a thermonuclear reaction, causing a runaway fusion process that tears the white dwarf apart. The explosion is spectacular, with a flash of light that can outshine an entire galaxy for a short period. Type 1a supernova are of great value to astronomers because they serve as standard candles for measuring cosmic distances. Their consistent peak brightness makes them invaluable tools for calibrating the scale of the universe and understanding its expansion. The second category of supernovae encompasses Type 2, Type Ib, and Type Ic supernovae, which all arise from the core collapse of massive stars. These stars are at least 8 times the mass of the Sun and go through a much different life cycle. As these stars age, their nuclear fusion processes progress through a series of stages. They begin by fusing hydrogen into helium, and then as the star grows older, it fuses heavier elements, eventually reaching iron. Iron, however, is a special case. Fusion of iron consumes more energy than it releases, which means the star can no longer maintain the internal pressure necessary to counterbalance its own immense gravitational pull. Without this pressure, the core collapses in on itself. This collapse triggers an explosive reaction that ejects the outer layers of the star outward in a violent supernova explosion. The remnants of the core may form a neutron star, or in the case of an even more massive star, collapse further into a black hole. The incredible power of these supernovae not only marks the death of the star, but also disperses essential elements into the universe. These explosions are responsible for creating many of the heavier elements, such as gold, platinum, and uranium, which are crucial for the formation of planets and life as we know it. Supernovae also offer deep insights into stellar evolution and cosmic element formation, but their impact doesn't end there. The remnants left behind, neutron stars and black holes, continue to be subjects of intense study. Neutron stars, for example, can become pulsars, rapidly rotating objects that emit beams of electromagnetic radiation. These pulsars act like highly accurate cosmic clocks, emitting regular pulses that allow scientists to test theories of general relativity, probe the structure of the universe, and even detect gravitational waves, a key prediction of Einstein's theory. Magnetars, a special class of neutron stars with the most intense magnetic fields known to exist in the universe, offer even more extreme conditions for study. These objects are key to understanding the behavior of matter under conditions that cannot be replicated on Earth, such as incredibly strong magnetic fields that influence the star's emissions and its interaction with the surrounding interstellar medium. The study of pulsars and magnetars not only sheds light on the behavior of matter in extreme environments, but also contributes to our understanding of fundamental physics. The mysterious properties of neutron-rich matter, as well as the dynamics that power these objects' emissions, have broad implications for nuclear physics, the equation of state for neutron stars, and our knowledge of the forces of nature that govern the universe. By observing the aftermath of supernova, scientists are uncovering the deepest mysteries of the cosmos. The fate of a star is determined by its mass. For stars like our Sun, the end is relatively gentle. As the star exhausts its hydrogen fuel, it swells into a red giant, fusing helium into carbon and oxygen. Eventually, the star sheds its outer layers into space, creating a beautiful planetary nebula. What remains is the hot core, a white dwarf, which slowly cools and fades over billions of years. However, for stars much more massive than the Sun, the ending is dramatically different. After fusing elements up to iron, these stars no longer generate enough pressure to balance the force of gravity. The core collapses catastrophically, leading to a supernova explosion, an event so powerful that it briefly outshines entire galaxies. Depending on the size of the remnant core, the outcome may be a neutron star, a dense object only a few kilometers across, or a black hole. In this universe of stars, explosions, and remnants, the forces of gravity and nuclear fusion are in constant balance, dictating the rise and fall of celestial bodies. The study of these extraordinary events not only helps us understand the nature of stars and their death throes, but also reveals the fundamental processes that have shaped the elements we are made of. In this way, the supernovae that end a star's life also spark the creation of the universe as we know it, offering a profound glimpse into the forces that govern the cosmos. The death of a star is one of the most awe-inspiring and mysterious events in the universe. But when that star is of a mass greater than our sun, or even when it collapses into a black hole, something much more extraordinary happens. These violent ends are not just cosmic spectacles, they play an essential role in the vast ongoing cycle of matter that drives the universe itself. Stars with massive masses are the cosmic factories, creating and dispersing elements heavier than helium, elements that become the building blocks for new stars, planets, and even the possibility of life. These explosive deaths release more than just light and heat. They distribute the very materials that shape the future of the cosmos, seeding distant corners of space with the raw ingredients for the next generation of stars and planets. What remains after such a cataclysm? Neutron stars and black holes, objects so dense and mysterious, they continue to confound and fascinate scientists to this day. Their extreme properties provide us with a glimpse into the hidden laws of physics, under conditions impossible to recreate here on Earth. In essence, the death of a star is not just an end. It is a crucial, transformative step in the endless cycle of the universe's birth, death, and rebirth. Neutron stars, formed from the remnants of massive stars that explode in a supernova, are the densest objects in the universe. When the core of a massive star runs out of nuclear fuel, gravity begins to take over, compressing the core to such an extent that protons and electrons merge, forming neutrons. This violent compression leads to a tiny, compact object, a neutron star, about 10 kilometers in radius, but with a mass 1.4 to 2.1 times that of the Sun. The result? A density so extreme that a single cubic centimeter of neutron star material weighs as much as Mount Everest. This unimaginable density is what makes neutron stars so fascinating to astronomers, as they exist at the precipice between being too small to form a black hole and too large to become a white dwarf. The formation of a neutron star is a delicate balance. If the remaining core has too much mass, it will collapse further, forming a black hole where not even light can escape. If the mass is insufficient, it will end up as a white dwarf. But for stars with masses between 8 and 25 times that of our Sun, their end result is a neutron star. This transformation is accompanied by a supernova explosion, one of the most energetic events in the cosmos. For a brief moment, these explosions can outshine an entire galaxy, releasing an immense burst of energy and sending shockwaves throughout the universe. Yet even in their final moments, these stars leave behind a wealth of knowledge. Neutron stars are magnetic powerhouses, their magnetic fields billions of times stronger than Earth's. Some spin incredibly fast, up to several hundred times per second, emitting beams of radiation from their magnetic poles. When these beams sweep past Earth, we detect them as regular pulses. These pulsars, as they are known, offer astronomers a unique opportunity to conduct experiments in the most extreme conditions imaginable: extreme gravity, intense magnetic fields, and rapid rotation, conditions that are simply unattainable on Earth. These pulsars become cosmic laboratories, enabling us to test theories about how matter behaves under conditions far beyond what we could ever replicate in a laboratory. Despite their seemingly simple nature, neutron stars hold the key to understanding the fundamental forces of the universe. Their extreme density, gravity, and speed provide scientists with a unique insight into the nature of matter and the fundamental laws of physics. These tiny remnants of massive stars offer a glimpse into a world where time and space are distorted, where the rules we take for granted on Earth break down, and where new physics may be hiding. Yet for all our advancements in astrophysics, predicting exactly when a star will go supernova remains one of the greatest challenges. Stars do not go supernova at a predictable, fixed moment. Instead, their life cycles unfold over millions of years, with the final supernova explosion taking place in the last few moments. Predicting this event is not simple. While scientists understand the general processes that lead up to a supernova, such as the fusion of heavier elements in the star's core, the exact timing of the explosion remains elusive. Observing signs like an increase in neutrino emissions or a sudden surge in the fusion of heavier elements gives us some hints, but pinpointing the precise moment when a star will die is still beyond our capabilities. As we continue to observe these spectacular cosmic events, we realize that the end of a star's life is not merely an end. It is part of an ongoing, dynamic cycle that shapes the universe as we know it. These violent, explosive events may seem destructive, but they are in fact the engines of creation, providing the raw materials for the next generation of stars, planets, and perhaps even life. But these signals, though subtle, often precede a celestial event by mere moments, leaving little time for timely warnings. From a human perspective, this presents a tremendous challenge. However, advancements in observational technologies, computer simulations, and our understanding of stellar physics are gradually improving our ability to model the life cycles of stars. More importantly, these innovations are helping scientists potentially forecast the fiery ends of these stars with greater accuracy. For instance, the study of red supergiants, the stellar progenitors of Type II supernova, has revealed fascinating pre-supernova changes in brightness and behavior. These observations suggest that the end stages of a star's life are far more complex and turbulent than previously thought. As research progresses, astronomers are working relentlessly to refine their models, striving for a future where predicting supernovae with greater precision becomes a reality. Such breakthroughs will provide deeper insights into the mechanisms of stellar evolution, ultimately enhancing our understanding of the cosmos. One crucial concept emerging from these studies is the Eddington limit, named after the British astrophysicist Sir Arthur Eddington. This theoretical limit serves as a cap on the luminosity or brightness a star can achieve while maintaining hydrostatic equilibrium. In simpler terms, the Eddington limit marks the delicate balance between the outward pressure of radiation from a star's light and the inward pull of gravity. If a star's luminosity exceeds this limit, the radiation pressure can overpower the force of gravity, potentially leading to the expulsion of the star's outer layers and significant mass loss. This phenomenon is not exclusive to stars. It also plays a pivotal role in understanding the behavior of accreting black holes and other astrophysical objects. For example, when material falls into a black hole, it heats up and emits radiation. If the accretion rate is high enough, the radiation's pressure can exceed the Eddington limit, effectively halting further material from falling into the black hole and limiting its growth. This concept helps astronomers predict the evolutionary paths of high-mass stars, black holes, and galaxies, allowing them to study some of the most energetic phenomena in the universe. By understanding the Eddington limit, scientists can unlock critical information about the dynamics of celestial bodies and their role in the ever-expanding universe. At the very heart of stars, a cosmic alchemy takes place, where lighter elements are transformed into heavier ones through the process of nuclear fusion. Deep within their scorching cores, where temperatures soar into the millions of degrees, hydrogen atoms fuse together to form helium. This process releases an enormous amount of energy, part of which radiates outward, lighting up the star. As stars age and their hydrogen fuel begins to deplete, they shift to fusing helium into heavier elements like carbon and oxygen. In more massive stars, the temperatures and pressures become intense enough to create elements as heavy as iron. However, producing elements heavier than iron requires energy beyond what the star can generate through fusion. This energy gap is closed during the star's final explosive moments, the supernova. These colossal explosions scatter the enriched material from the star's core across the cosmos, fertilizing the universe with the elements needed for new stars, planets, and eventually life. Every atom of carbon, every speck of iron, and every fragment of gold in our bodies exists because of the immense forces of its own existence, transmuted simpler elements into the complex and beautiful diversity of the periodic table. Astronomers also employ a variety of ingenious methods to detect exoplanets, planets orbiting stars beyond our solar system. One of the most pivotal techniques is the transit method. This technique is based on observing a star's light dimming slightly when an exoplanet passes in front of it, momentarily blocking a fraction of its light. While this method confirms the existence of an exoplanet, it also provides valuable information about its size, orbit, and composition, paving the way for even deeper exploration of planets outside our solar system. Through these methods, scientists are uncovering the vast potential for life beyond Earth and uncovering the mysteries of the universe one discovery at a time. But it can also offer vital clues about the planet's size, as the amount of starlight blocked provides significant insights. Another fundamental approach to understanding distant worlds is the radial velocity method, which observes the subtle wobbling of a star caused by the gravitational tug of an orbiting planet. This wobble causes a shift in the star's light spectrum known as the Doppler effect, which astronomers can detect. While this method reveals a planet's mass, it's the combination of radial velocity and transit techniques that allow for a fuller understanding of an exoplanet's characteristics, including its density, which provides clues to its internal composition. These methods, along with others, have led to the discovery of thousands of exoplanets, an array of celestial worlds ranging from enormous gas giants larger than Jupiter to rocky planets that may one day host life. These worlds, tucked away in the vast reaches of our galaxy, have expanded the frontier of planetary science. One of the most compelling aspects of this search is the habitable zone, often referred to as the Goldilocks zone, a region around a star where the conditions might be just right, not too hot nor too cold for liquid water to exist on a planet's surface. Water, as we know, is a key ingredient for life, making the habitable zone a region of immense interest. For a planet within this sweet spot, the temperature is perfect for liquid water to persist, providing the conditions that could support the development and sustainment of life. However, the boundaries of this habitable zone are not fixed. They vary depending on the size and temperature of the star. Larger, hotter stars have their habitable zones further out, while smaller, cooler stars have theirs much closer. Over the years, the search for exoplanets within these habitable zones has intensified, with astronomers particularly focused on identifying Earth-sized worlds that might mimic the conditions of our own planet. The discovery of such worlds brings us tantalizingly closer to the possibility of life beyond our solar system. This ongoing quest not only helps us understand the vastness and diversity of the universe, but also illuminates the delicate balance that has allowed life to thrive on Earth. Among the thousands of exoplanets discovered, a few stand out due to their sheer oddity, planets that challenge our understanding of planetary systems. One such world is HD 199733b, known as the Blue Planet, not because of oceans like Earth's, but because of its glass rain. The winds on this planet reach speeds of over 5,000 miles per hour, a harsh environment indeed. Then there's 55 Cancri e, a planet that orbits so close to its star that temperatures might be high enough to turn carbon into diamond, making this world glitter with the brilliance of precious gems. Another mind-boggling discovery is Tar ES2b, the darkest planet known to date. It reflects less than 1% of the light it receives, making it darker than coal due to its light-absorbing atmosphere. Equally fascinating is Kepler-16b, a planet with two suns, an extraordinary scenario straight out of science fiction, yet it exists in reality. These planets defy the conventional characteristics we once assumed were typical for planets in our solar system, expanding our understanding of what is possible in the universe. The intriguing possibility of life existing on planets orbiting binary star systems, where two stars are locked in a gravitational dance, has captivated scientists and the public alike. Once a concept relegated to the realm of science fiction, This idea has gained serious scientific attention with the discovery of planets residing in such systems. The dynamics of binary star systems add complexity to the conditions on orbiting planets, influencing their climates and potentially their habitability. Depending on the orbits of the stars and the planet itself, these systems can produce a wide variety of environmental conditions, which could significantly affect the stability of the climates needed for life. Nevertheless, theoretical models suggest that stable habitable zones can exist in binary systems, particularly around circumbinary planets, those that orbit both stars at a sufficient distance. These models offer exciting possibilities that such planets could maintain conditions suitable for life despite the complex gravitational forces at play. The discovery of Kepler-16b, a circumbinary planet residing in a stable orbit within its star's habitable zone, has fueled further optimism about the potential for life in these extraordinary planetary systems. As research continues, our understanding of habitability is evolving, suggesting that life in the universe may be more diverse and widespread than we previously imagined. Planetary systems are born from the remnants of giant molecular clouds, the cold, dense regions in space where stars are born. A disturbance, possibly caused by a nearby supernova, triggers the collapse of a portion of the cloud. As the cloud collapses under its own gravity, it begins to spin and flatten into a spinning disk of gas and dust, known as a protoplanetary disk. At the center of this swirling maelstrom, material gathers to form a new star, while the surrounding dust and ice particles collide and stick together, gradually growing into larger bodies through a process called accretion. These particles form planetesimals, the building blocks of planets, which continue to collide and merge over millions of years, eventually forming fully fledged planets. The planets then clear their orbits of debris, and the solar system settles into a stable configuration. This process of planetary formation is thought to occur universally across the galaxy, explaining the incredible variety of planetary systems that astronomers discover. The intricate dance from the collapse of a gas cloud to the emergence of a star with orbiting planets showcases the awe-inspiring processes that govern our universe. Rogue planets, those mysterious wanderers drifting through space without a star to orbit, offer remarkable insights into the mechanisms of planetary formation and the dynamics of young solar systems. These free-floating bodies are believed to form in one of two ways, either as planets ejected from their original solar systems due to gravitational interactions, or as standalone objects that form directly from a collapsing cloud of gas and dust, much like a star. These rogue worlds, drifting through the void without the warmth or light of a star, challenge our understanding of planetary evolution, yet they highlight the incredible diversity of planetary types in the universe. Each discovery adds another layer to our comprehension of how planets form and evolve, continuing to inspire the imagination and curiosity of scientists and stargazers alike. Rogue planets, though not possessing the critical mass required for nuclear fusion, offer a fascinating glimpse into the complexity of planetary formation. Their existence challenges and enriches our understanding by highlighting the unpredictability and dynamic interactions within solar systems. These rogue planets, wandering the cosmos without a host star, suggest that solar systems are far more volatile than we once believed, with forces at play that can dramatically alter the destinies of planetary bodies. Their very presence forces us to reconsider the conventional models of planetary evolution. What's even more intriguing is the possibility that rogue planets could form in isolation, similar to stars. This expands the scope of our search for planetary bodies, opening up new avenues of exploration into environments that we might have otherwise overlooked. The study of these cosmic nomads could provide us with critical insights into the early universe, shedding light on the conditions that may have existed in the infancy of our own solar system. By investigating their characteristics, we stand to learn not only about the planets themselves, but also about the processes that govern the formation of stars and planets throughout the galaxy. Super-Earths, a particular class of exoplanets, have mass larger than Earth's, but significantly smaller than that of ice giants like Neptune or Uranus. These planets typically range between 1 to 10 times the mass of Earth. But it is not just their size that makes them so captivating. it is the diversity of conditions they may present. Super-Earths could have thick atmospheres, strong magnetic fields, and higher surface gravity, all of which could influence their geology, climate, and potential habitability. These planets provide an opportunity to study environments that differ drastically from those on Earth, forcing us to rethink what makes a planet suitable for life. Some super-Earths exist within the habitable zone of their stars, an area where conditions are right for liquid water to exist on the surface. However, even these super-Earths may offer conditions vastly different from anything seen in our solar system. Imagine planets where oceans cover every inch of land, or dry, rocky worlds with little or no water. Moreover, super-Earth's size could help them retain atmospheres more effectively against the harsh stellar winds that would otherwise strip away their atmospheres over time. This makes them prime candidates for study, offering unique environments that could harbor life, or perhaps reveal the secrets of life's building blocks. The variety of super-Earths discovered so far, some boiling with surface temperatures, others potentially harboring oceans beneath thick ice, challenges our preconceived notions of what makes a planet capable of supporting life. The study of exoplanet atmospheres involves sophisticated techniques that reveal a wealth of information about these distant worlds. One method, transmission spectroscopy, analyzes how a planet's atmosphere interacts with the light from its host star. When a planet transits in front of its star, some of the starlight filters through the atmosphere, allowing astronomers to detect specific absorption lines that correspond to different gases. Another method, emission spectroscopy, occurs when a planet passes behind its star, creating a secondary eclipse. By comparing the amount of light emitted by the planet when it is visible versus when it is obscured, scientists can infer details about the planet's temperature and atmospheric composition. Finally, reflected light spectroscopy measures the light reflected off a planet's atmosphere, providing additional clues about its makeup. These techniques, requiring incredibly sensitive instruments, are often carried out by space telescopes like Hubble and the James Webb Space Telescope. Using these instruments, astronomers have been able to identify components like water vapor, methane, and other gases in the atmospheres of exoplanets. These discoveries are vital for understanding the diversity of worlds beyond our solar system and for identifying those that may harbor the conditions necessary for life. Speculation about a ninth planet in our own solar system, often referred to as Planet 9, has captured the imaginations of both scientists and the public alike. This hypothetical planet is believed to exist far beyond Neptune in the icy reaches of the Kuiper Belt, a region filled with dwarf planets and icy objects. The idea of Planet 9 arises from unusual orbital patterns observed in some trans-Neptunian objects, TNOs. These orbits appear to be influenced by the gravitational pull of an unseen object, prompting the theory that a large, as yet undiscovered planet might exist in that distant region. If Planet 9 exists, it could be many times the mass of Earth, potentially comparable to Neptune or Uranus. Its discovery would have profound implications for our understanding of the solar system's formation and evolution. Despite numerous searches and observations, Planet 9 has yet to be found, and its existence remains inferred solely through indirect evidence. However, the ongoing search, driven by advanced telescopes and observational techniques, demonstrates the relentless curiosity that fuels astronomical discovery. Whether or not Planet 9 is ever discovered, the pursuit itself highlights the vastness of our solar system and the endless possibilities for future exploration. The Goldilocks principle, when applied to the search for habitable exoplanets, is central to the quest for worlds that are just right for life as we know it. This principle is linked to the concept of the habitable zone around stars, where conditions are neither too hot nor too cold, allowing liquid water to exist, one of the key ingredients for life. The term draws from the well-known fairy tale of Goldilocks and the Three Bears, where Goldilocks favors things that are not too extreme, but instead are perfectly balanced. In the search for exoplanets that could potentially harbor life, scientists focus on identifying planets located within their star's habitable zone. These are the regions where conditions could be just right, where liquid water could persist on the surface without boiling away or freezing solid. However, The Goldilocks principle is more than just about temperature. It speaks to the search for worlds that strike the right balance, not only in terms of water, but in terms of everything that makes a planet suitable for life. As we continue to explore distant exoplanets and speculate about the existence of new ones in our own solar system, the possibilities for discovery grow ever more exciting. Each breakthrough, whether in the study of rogue planets, super-Earths, or the search for Planet 9, brings us one step closer to unraveling the mysteries of the universe and understanding the forces that shape the worlds we call home. The universe, with its vast array of planets, continues to inspire awe and wonder, fueling our desire to explore and discover. But when we delve into the fascinating world of exoplanets, we see a remarkable pattern emerge. These planets, floating in the vastness of space, must exist in a delicate balance. Too close to their parent star, and they risk being scorched by extreme temperatures that could vaporize water and erase any chance for life. Too far, and they enter the freezing depths of space, where water could solidify into ice, making the environment inhospitable. The Goldilocks principle, however, provides a fundamental framework for understanding this balance. It's not just about temperature. Other crucial factors come into play, such as a planet's size. A planet's size directly influences its ability to retain an atmosphere, which is essential for sustaining life. Furthermore, the composition of a planet plays a vital role. A planet rich in certain elements will foster geological activity, which in turn supports the recycling of vital gases like carbon dioxide and oxygen, key to maintaining life-supporting processes. As we explore exoplanets, we must also turn our gaze to the immense galaxies that house them. Galaxies, those colossal clusters of stars, gas, and dust, have evolved over billions of years. They are constantly changing, formed through a complex dance of gravitational forces and cosmic interactions. The birth of galaxies can be traced back to the earliest moments after the Big Bang. Dark matter, invisible yet abundant, clumped together under the influence of gravity, creating a scaffolding around which ordinary matter, atoms of gas and dust, converged. From these clouds, stars formed, eventually giving rise to the galaxies we observe today. Galaxies are not static, they are dynamic entities. As galaxies grow, they absorb gas from the surrounding intergalactic medium, which fuels new star formation. Collisions between galaxies are also a defining feature of their evolution. These cosmic crashes often trigger bursts of star formation, warp the structure of the galaxies involved, and change the course of their development. For example, astronomers predict that our own Milky Way galaxy will eventually collide with the Andromeda galaxy, giving birth to a new elliptical galaxy in the process. This evolution isn't just driven by external interactions. At the heart of most galaxies lies a supermassive black hole, a mysterious and powerful entity that influences the galaxy's life cycle. These black holes regulate star formation through energetic feedback loops, a process that can either quench or stimulate the birth of new stars. Understanding the formation and evolution of galaxies is a multifaceted journey, one that connects the birth of the universe to the cosmic drama playing out in real time. From their chaotic beginnings to their complex interactions with other galaxies, the story of galaxies is one of constant change and adaptation. The shape of a galaxy, a characteristic that has intrigued astronomers for centuries, is one of the most visible indicators of its history. Galaxies come in various forms: elliptical, spiral, and irregular, each shaped by a unique combination of internal and external factors. Elliptical galaxies, for example, range from nearly spherical to elongated ellipses. These galaxies have a smooth, featureless appearance because their stars move in random directions with no defined spin axis. In contrast, spiral galaxies, like our Milky Way, possess flat, disc-like shapes with striking spiral arms. These arms are not just beautiful, they are the result of differential rotation within the galaxy, where different parts of the galaxy spin at different speeds, organizing the gas and dust into spirals through gravitational forces. Irregular galaxies, which defy classification as either elliptical or spiral, often appear chaotic. Their unusual shapes arise from interactions with other galaxies, which can distort their structure, strip away material, and trigger bursts of star formation. The resulting appearance is often messy, but uniquely captivating. This vast and ever-changing dance of galaxies, exoplanets, and cosmic forces reminds us of the beauty and complexity of the universe. Every galaxy, every exoplanet is a part of an ongoing cosmic story, one that spans billions of years and continues to unfold before our eyes. Furthermore, the presence of a dark matter halo surrounding galaxies plays a pivotal role in shaping their formation. This unseen yet powerful force provides a gravitational framework, influencing the movements of stars and the mass gaps within galaxies. In essence, the shape and structure of a galaxy are the intricate result of a multitude of factors: its internal dynamics, the profound gravitational pull of dark matter, and its cosmic interactions with neighboring galaxies. These elements work together, crafting galaxies into what we observe today. Galaxies are constantly colliding, driven by the unrelenting force of gravity acting across vast cosmic distances. The immense gravitational pull exerted by both galaxies and their surrounding dark matter halos can draw these enormous of stars toward each other, despite the universe's overall accelerating expansion. On larger cosmic scales, the expansion of the universe dominates, yet locally, within galaxy clusters and superclusters, gravity can overpower this expansion, creating conditions ripe for galactic interactions and collisions. When galaxies collide, the resulting event is nothing short of dramatic and unfolds over millions to billions of years. Though galaxies contain countless stars, the actual collisions between stars are remarkably rare, owing to the vast distances that separate them. Instead, the interstellar gas and dust within galaxies become the main actors in these galactic encounters. As these gas clouds collide, they are compressed and undergo gravitational collapse, triggering the rapid formation of new stars. This process can lead to explosive bursts of star creation, reshaping the galaxy's stellar composition. The gravitational forces at play between colliding galaxies are not only responsible for triggering star formation, but also for distorting the galaxies themselves. Tidal forces can stretch the galaxies, pulling out long tails of stars and gas, or they can create fascinating structures like rings or shells. Over time, these interacting galaxies may eventually merge into a single, more massive galaxy. The characteristics of the resulting galaxy depend heavily on the masses and original structures of the colliding galaxies. For instance, when two similarly sized spiral galaxies collide, the outcome may be the creation of an elliptical galaxy, vastly different from its spiral predecessors. Supermassive black holes, which reside at the centers of most galaxies, also play a critical role during galactic collisions. These colossal black holes can grow by accreting the gas that is disturbed by the merger. If both galaxies involved in the collision harbor supermassive black holes, these titanic objects may spiral toward each other, eventually merging into one. This cataclysmic event would release an unimaginable amount of energy and potentially create gravitational waves that ripple through the fabric of space-time. Galactic collisions are, therefore, a crucial process in the evolution of the universe, shaping the structure of galaxies and driving their continuous transformation through cosmic time. The title of the largest galaxy in the known universe, according to current astronomical observations, belongs to IC 1101, located roughly 1 billion light-years away at the center of the Abell 2029 galaxy cluster. IC 1101 is an enormous elliptical galaxy that challenges comprehension with its sheer scale. Spanning about 4 million light-years from end to end, it is nearly 40 times larger than the Milky Way, which measures only about 100,000 light-years across. With this colossal size, IC 1101 contains hundreds of trillions of stars, far surpassing the number found in our own galaxy. The staggering size of IC 1101 is believed to be the result of numerous galactic mergers that have occurred over billions of years. In the dense environment of a galaxy cluster, such mergers are much more common, enabling a galaxy like IC 1101 to grow to its truly gargantuan proportions. This colossal scale offers a fascinating glimpse into the complex processes that drive galaxy formation and evolution on the grandest scales. It underscores the dynamic and ever-changing nature of the cosmos, offering a unique window into the forces that shape our universe. The story of IC 1101 highlights the incredible scale of the universe and the ongoing evolution of galaxies. This process is a testament to the immense forces at play in the cosmic dance, where galaxies collide, merge, and transform over eons. In the vastness of space, these events are but one chapter in the eternal unfolding of the universe's story. Those colossal congregations of galaxies, bound together by the invisible yet undeniable force of gravity, form a stunningly intricate tapestry that stretches across the cosmos. Think of these superclusters as the universe's grand urban centers, vast hubs where galaxies, like our very own Milky Way, reside. But these immense structures aren't just arbitrary arrangements. They are the architects of cosmic order, dictating not only how galaxies are distributed across the universe, but also how they move through the great expanse of space. At the heart of this structure lies the cosmic web, a vast network of filaments made of dark matter that spans the entire universe. It is within this invisible framework that superclusters come to life, marking the largest and most profound structures in the known universe. These superclusters, with their immense gravitational pull, have the power to warp the very fabric of space-time, bending the path of light itself. This phenomenon, known as gravitational lensing, offers scientists a unique window into the distant, often hidden corners of the universe. It allows us to observe galaxies, stars, and even the farthest-reaching cosmic phenomena, some of which would otherwise remain veiled in darkness. Through gravitational lensing, we gain not only an understanding of the distribution and density of dark matter, but also invaluable insights into the universe's expanding nature. The light from faraway galaxies carries with it information about the universe's expansion rate, while the effects of mysterious dark energy, this invisible force accelerating the cosmos's expansion, are brought to the forefront. By unraveling the intricate role played by these galactic superclusters, we take a deeper step into understanding the universe, revealing a vast interconnectedness that binds everything together, from the smallest particle to the most gigantic structures ever observed. However, amidst the grandiosity of superclusters, one crucial yet often overlooked component plays an essential role: the intergalactic medium, IgM. The IgM, a diffuse gas that fills the space between galaxies, may seem like an invisible passive entity, but its significance cannot be overstated. It acts as a cosmic reservoir, holding the raw materials necessary for the formation of stars, planets, and even life. Despite its ethereal and seemingly insubstantial nature, the IgM is an active participant in the grand cosmic dance. As galaxies drift through this expansive sea of gas, they interact with the IgM in a complex and dynamic exchange. Galaxies draw in fresh, pristine gas from the IgM to fuel new star formation, while simultaneously releasing the remnants of past stellar activity, elements and particles forged through the cosmic alchemy of star death. This ongoing recycling process enriches the IgM, ensuring that the gases within continue to evolve chemically, contributing to the ever-changing landscape of the universe. Additionally, the IgM is intricately woven into the filaments of the cosmic web, which serves as the scaffolding for the universe's largest structures. By studying the IgM, we gain precious clues about the universe's early epochs, unlocking secrets about the formation of the first galaxies and deepening our understanding of the cosmos itself. In essence, the IgM is the connective tissue of the universe, an invisible yet indispensable component that fuels the birth and growth of galaxies. It is within this cosmic medium that the first stars and galaxies took form, making it a fundamental player in the ongoing evolution of the universe. On another scale, quasars, short for quasi-stellar radio sources, emerge as some of the most remarkable and awe-inspiring phenomena in the universe. These cosmic beacons shine brightly, often outshining entire galaxies with their brilliance. At the heart of each quasar lies a supermassive black hole, millions to billions of times the mass of our sun, relentlessly consuming surrounding gas, dust, and even stars. As this material spirals inward, it forms an accretion disk, heating to incredible temperatures and emitting immense amounts of light and energy. But quasars are not just about brilliance. They are also among the most distant objects we can observe. Their light, which has traveled for billions of years to reach us, acts as a cosmic time capsule. Through this light, we gain insights into the conditions and processes that shaped the early universe. Quasars also serve as natural laboratories, providing a unique opportunity to study the extreme environments surrounding supermassive black holes and their impact on the galaxies that host them. Furthermore, quasars play a pivotal role in mapping the vast cosmic web. Their light, traveling across unimaginable distances, can illuminate the otherwise invisible filaments of gas that stretch across the universe. By shining a light on these dark and unseen structures, quasars help scientists trace the vast network of cosmic connections that bind the universe together. Thus, quasars are not only spectacular and luminous phenomena, but also key tools in understanding the structure and history of the universe itself. In the grand tapestry of the cosmos, these colossal structures from superclusters to quasars are more than just isolated entities. They are the threads that weave the intricate design of the universe, revealing the profound interconnectedness of all things. As we continue to explore and understand these celestial wonders, we unlock the mysteries of the cosmos, one discovery at a time. But also, in the vast expanse of the universe, where we search for answers to the most profound mysteries, there are cosmic phenomena that act as crucial tools for understanding the grandest scales and earliest epochs. Among these, active galactic nuclei, AGN, and quasars stand out as luminous beacons at the centers of galaxies, each powered by supermassive black holes, consuming material from their surroundings. These celestial powerhouses, though sharing a common origin, differ significantly in terms of luminosity and the scale at which they are observed. Quasars represent the extreme end of the AGN spectrum, emerging as the most powerful and distant members of this cosmic family. Their energy is so intense that they can outshine entire galaxies, making them visible across vast cosmic distances. Their light spans the electromagnetic spectrum from radio waves to X-rays, and with their extraordinary luminosity, quasars provide a window into the farthest reaches of space. AGN, while similar in their black hole-driven energy, encompass a broader range of objects, some of which are less luminous, such as Seyfert galaxies and radio galaxies. The variation in appearance, luminosity, and observable traits among AGN can be attributed to several factors, including the mass of the black hole, the rate at which material is accreted, and the orientation of the galaxy relative to our line of sight. The study of quasars and other AGN is not just a pursuit of fascinating celestial objects, but also a critical probe into the mechanics of galaxy evolution and the growth of supermassive black holes over cosmic time. These phenomena help scientists decipher the intricate processes that shaped galaxies and the black holes at their cores. However, the story of the cosmos doesn't end with quasars. The youngest galaxies, observable in the farthest reaches of the universe, represent a key chapter in understanding the origins of the cosmos. These distant galaxies, viewed as they were only a few 100 million years after the Big Bang, offer an invaluable glimpse into the era known as the Cosmic Dawn. During this time, the first stars and galaxies emerged, igniting the universe for the first time. Observing these infant galaxies is a formidable challenge due to their immense distance and faintness. Yet, with the advent of cutting-edge technology such as the James Webb Space Telescope, JWST, astronomers are now able to push the boundaries of discovery further back in time than ever before. The JWST, with its unparalleled resolution and sensitivity in the infrared spectrum, is capable of detecting the faint light from these early galaxies, which has been stretched into longer wavelengths due to the expansion of the universe. These observations allow scientists to study the composition, formation, and evolution of the earliest galaxies, providing crucial insights into the processes that laid the groundwork for the universe as we know it. Far from being mere smudges of light, these galaxies represent the seeds from which the complex structure of the modern cosmos grew, making their study essential for understanding our cosmic origins. Yet beyond these distant galaxies lies another mystery, the enigmatic dwarf galaxies. Despite their diminutive size, dwarf galaxies pose a series of perplexing questions, particularly regarding their dark matter content. These galaxies, though small in size, are disproportionately rich in dark matter, the elusive substance that neither emits nor absorbs light. This makes them crucial laboratories for studying the nature and distribution of dark matter. Additionally, the survival of these small galaxies in the vicinity of massive neighbors, like the Milky Way, presents another cosmic riddle. Theoretical models predict that these smaller galaxies should be torn apart by the gravitational forces of their larger neighbors. Yet they persist, suggesting that there may be forces or processes at play that we do not fully understand. The star formation history within dwarf galaxies adds another layer of complexity. Some exhibit bursts of star formation, followed by extended periods of quiescence, defying the simplistic models of galactic evolution. This raises questions about the factors influencing star formation in such small systems. Furthermore, the disparity between the observed number of dwarf galaxies and the predictions from cosmological models, known as the missing satellites problem, points to potential gaps in our understanding of galaxy formation and dark matter's role in shaping the universe. Yet, within these cosmic puzzles lies the potential for profound revelations about the fundamental principles that govern the universe's structure and evolution. As scientists continue to explore the mysteries of dwarf galaxies, they bring us closer to unlocking the secrets of the cosmos. Meanwhile, another bold theory, string theory, has emerged as a potential framework for understanding the deepest mysteries of the universe. String theory, which seeks to unify quantum mechanics and general relativity, proposes that the most elementary particles, once thought to be point-like objects, are actually tiny vibrating strings. Just as different strings on a violin produce distinct notes, the vibrations of these cosmic strings determine the properties of particles, such as mass and charge. At the heart of string theory lies the possibility of extra dimensions beyond the familiar four, 3 dimensions of space and 1 of time. These extra dimensions, which may be compactified and curled up at minuscule scales, could provide the key to unifying all forces of nature into a single theoretical framework. This concept opens the door to understanding the behavior of particles at the quantum level and the structure of the universe on the grandest scales. One of the most exciting implications of string theory is its suggestion of a multiverse, an infinite number of universes, each with its own set of physical laws and constants. This idea challenges our understanding of the very nature of reality, proposing that our universe is just one of many, each potentially vastly different from the others. While string theory remains largely theoretical and lacks direct experimental evidence, it continues to inspire physicists, offering elegant solutions to some of the most perplexing problems in science. As it stands at the frontier of our understanding of the cosmos, string theory offers a potential glimpse into the ultimate fabric of space-time and matter, weaving together the disparate threads of our universe into a unified picture of reality. Through this lens, we may one day uncover the true nature of existence itself. The question remains, though, will we ever truly understand the full scope of our cosmic origins? But rather, just one of an immense number, or even an infinite array of universes, this fascinating notion has ignited the exploration of several competing theories, each offering a unique perspective on the structure and origins of these multiple universes. The concept of the multiverse has evolved into one of the most mind-boggling and perplexing puzzles in modern cosmology. These theories span a wide range of ideas, each striving to explain the possible existence of parallel universes beyond our own. One prominent theory, the bubble universe theory, is a direct outgrowth of the concept of eternal inflation. This theory suggests that within the vast expanse of space, different regions of space-time have expanded at varying rates. Some regions expanded so rapidly that they formed bubbles, each with its own set of conditions that allowed galaxies, stars, and potentially life, much like our own universe, to form. In this view, each bubble represents a separate universe, entirely distinct from others, governed by its own physical laws and constants. Think of it like bubbles in a cosmic foam, each one a self-contained reality, popping in and out of existence over infinite time. In contrast, the many worlds interpretation of quantum mechanics provides a completely different take on the multiverse. According to this interpretation, every quantum event, every decision point, no matter how trivial, results in the splitting of the universe into multiple parallel realities. Every possible outcome of every decision that could ever occur does, in fact, occur in some alternate universe. In this framework, the multiverse is an ever-expanding tree, with each branching reality leading to a new universe, creating a nearly infinite network of possibilities. In essence, every what-if scenario has its own parallel universe, playing out its unique story. Then there's string theory, which suggests that the fundamental building blocks of the universe aren't particles, but tiny vibrating strings. These strings can vibrate in different ways, and the different modes of vibration give rise to different properties of particles, and, consequently, entire universes. According to this theory, the landscape of possible universes is not only vast, but incomprehensibly varied. Each universe has its own set of physical laws and constants determined by the way its strings vibrate. This idea pushes the boundaries of what we understand as reality, suggesting that an entire multiverse could be shaped by the unseen vibrating strings at the very heart of matter. The holographic principle introduces another radical possibility. It proposes that what we perceive as the three-dimensional universe is actually a projection, much like a hologram, encoded on a distant two-dimensional surface. In this model, our entire reality, from the stars in the sky to the molecules that make up our bodies, is simply a projection of information. But here's the kicker. If this projection exists, it's possible that many such projections exist simultaneously, each one representing a distinct universe, all contained on the same distant surface. This mind-bending theory challenges our very perception of reality and suggests that multiple universes could coexist as holographic projections, each distinct yet interconnected. Despite the compelling nature of these theories, the scientific consensus on the reality of the multiverse remains elusive. The primary obstacle lies in the significant challenge of obtaining empirical evidence to support or refute these ideas. After all, how does one measure something that lies beyond the observable universe? Nevertheless, the exploration of these theories continues to push the boundaries of physics, cosmology, and our understanding of the universe's very nature. Each new hypothesis brings us closer to answering fundamental questions about the origins of reality, even as it opens up new, tantalizing possibilities. At the very core of this debate lies quantum entanglement, a phenomenon that occurs when pairs or groups of particles interact in such a way that the state of one particle becomes intrinsically linked to the state of another, no matter the distance between them. This seemingly magical connection persists even if the entangled particles are light years apart. Albert Einstein famously dubbed this spooky action at a distance because it seemed to defy the established laws of physics. Yet, quantum entanglement has been experimentally confirmed and now plays a central role in our understanding of quantum mechanics. The implications of quantum entanglement reach far beyond the microcosm of individual particles. In recent years, theoretical physicists have proposed that the phenomena of quantum entanglement could be linked to the very fabric of spacetime itself. One fascinating proposition suggests that entangled particles might create tiny invisible wormholes, shortcuts through the fabric of space and time that could connect distant regions of the universe. This idea arises from the belief that the geometry of spacetime, as described by general relativity, could emerge from the quantum entanglement of particles. Essentially, the deep, fundamental connections between entangled particles might be the very threads that weave together the cosmic fabric of spacetime. Although the concept of quantum entanglement affecting spacetime remains speculative and lies at the cutting edge of theoretical physics, it represents one of the most ambitious efforts to reconcile the laws of the very large, general relativity, with those of the very small, quantum mechanics. If these ideas were to be proven true, they would not just revolutionize our understanding of how the universe works, they would fundamentally change our grasp of reality itself. The intersection of quantum mechanics and general relativity could hold the key to unlocking the deepest secrets of the universe, bringing us closer to an ultimate theory of everything. But also open up new possibilities for understanding the mysteries of black holes, the nature of the cosmos, and the fundamental forces that govern reality. The discovery of dark energy, the mysterious force that drives the accelerated expansion of the universe, has profoundly puzzled cosmologists since its observation in the late 1990s. Despite being incorporated into the standard model of cosmology as a significant component, dark energy's true nature remains elusive, and alternative explanations have emerged, challenging and expanding our understanding of the universe's evolution. One such alternative lies in the modification of gravity at cosmological distances. This approach suggests that Einstein's theory of general relativity, which describes gravity as the curvature of spacetime caused by mass, might not operate the same way on the grand scales of the universe as it does in more localized contexts, such as our solar system. Theories like modified Newtonian dynamics, MOND, and its relativistic extension, tensor vector scalar gravity, TVS, propose adjustments to how gravity behaves over vast distances, potentially negating the need for dark energy to explain the observed acceleration of cosmic expansion. These theories introduce an entirely new perspective, one that challenges our long-held understanding of the force that shapes the cosmos. Another compelling alternative lies in the concept of vacuum energy. Unlike the dark energy proposed to permeate space uniformly, vacuum energy is the energy inherent in the fabric of space itself. Some physicists explore the idea that this vacuum energy is dynamic, changing over time and leading to variations in the rate of the universe's expansion throughout its history. This perspective delves deep into quantum field theory and the properties of the quantum vacuum, opening the door to a range of new possibilities. If the vacuum energy isn't constant but fluctuates, it could mean that the universe's expansion rate has changed in different epochs of its existence, providing a potential key to unlocking the underlying mechanisms of cosmic evolution. Additionally, the inhomogeneous cosmology models, such as those based on the Lemaitre-Tolman-Bondi (LTB) void models, propose a radically different explanation. According to this view, the apparent acceleration of the universe's expansion is an illusion caused by our position within a vast underdense region of the cosmos. The uneven distribution of matter on large scales distorts our measurements of cosmic expansion, making it appear as though the universe is accelerating more in some directions than others. This theory challenges our assumptions about uniformity in the universe and suggests that the very nature of cosmic expansion might be far more complicated than we have imagined. While none of these alternatives has yet displaced the dark energy paradigm, they play a crucial role in pushing the boundaries of theoretical physics and cosmology. These competing theories force scientists to refine their methods, develop more precise measurements, and build increasingly sophisticated models. In doing so, they drive our collective quest to understand the most profound mysteries of the universe, the very forces that shaped it, the laws that govern its expansion, and the complexities of its hidden dimensions. The anthropic principle adds yet another layer to this exploration of the cosmos. This philosophical consideration seeks to explain the observed values of fundamental physical and cosmological constants in terms of human existence. It posits that the universe's laws, constants, and initial conditions appear finely tuned to allow for the emergence of life, especially human life as we know it. The principle takes various forms, ranging from the weak anthropic principle, which simply observes that the universe must allow for our presence because we are here to observe it, to the strong anthropic principle, which suggests that the universe is somehow compelled to bring about life. One of the main contexts in which the anthropic principle is invoked is in dealing with the fine-tuning problem. This problem observes that many of the universe's fundamental constants, such as the strength of gravity or the values of fundamental particles, masses, fall within a very narrow range. Change these values by even a slight margin, and the universe could be an inhospitable place, one where complex atoms couldn't form, stars wouldn't ignite, and conditions necessary for life wouldn't exist. The delicate balance of these constants suggests a universe fine-tuned to support life, making it seem as though the cosmos is designed with purpose. However, critics of the anthropic principle caution against its tautological nature, warning that it might stifle further investigation into cosmological mysteries by offering what appears to be a convenient explanation for the fine-tuning of the universe. Supporters, on the other hand, argue that it provides a crucial framework for understanding why the universe is the way it is and why life can emerge in such a seemingly improbable setting. These alternative theories, the exploration of vacuum energy, the potential modifications to gravity, and the contemplation of the anthropic principle all contribute to the ongoing journey of understanding the vast, complex, and mysterious universe in which we live. The questions of cosmic expansion, the force of gravity, and the fine-tuning of the laws of physics are not just academic. They are at the heart of our search for meaning and understanding in the cosmos. The search continues, driving human curiosity, exploration, and the quest for knowledge into uncharted territories. However, one might argue that the anthropic principle offers a crucial lens through which we can better comprehend why the universe appears as it does. It encourages the search for alternative explanations, such as the multiverse theory, where this principle finds its statistical foundation. In a cosmos teeming with an infinite number of universes, each with distinct physical parameters, it becomes unsurprising that at least one, like ours, possesses the right conditions to support life. Despite the varying opinions on its usefulness and philosophical significance, the anthropic principle undeniably sparks thoughtful debates in modern cosmology, urging us to rethink the very nature of the universe and our place within it. At the intersection of these debates lies a provocative and increasingly relevant theory, the idea that our universe might actually be a simulation. What was once the stuff of science fiction has evolved into a serious academic topic. The hypothesis proposes that everything we perceive, every event, experience, and object, could be part of an artificially created reality, meticulously crafted by a highly advanced civilization. This civilization would possess computational power far beyond our current capabilities, potentially capable of simulating entire universes down to the quantum level. The foundation for this idea can be traced back to our own technological advancements, such as the rapid evolution of video games and virtual reality environments. From rudimentary graphics to immersive, hyper-realistic experiences, these developments offer a glimpse into a future where such simulations could be the norm. Nick Bostrom's famous simulation argument posits that at least one of the following statements must be true. Either most civilizations at our level of technological progress go extinct before achieving the capability of creating reality-simulating technologies, or if they do reach this level, they choose not to run simulations of their evolutionary histories. Alternatively, it could be the case that we are, in fact, being inside a computer simulation. Proponents of this hypothesis point to peculiar phenomena in quantum mechanics, such as particles existing in a state of superposition until observed, as potential evidence of a simulated reality. In this view, the universe operates much like a video game, where its detailed resolution is only rendered when there is an observer. Despite its fascinating premise, the simulation hypothesis faces significant skepticism, particularly when it comes to empirical proof. How can we, as inhabitants of a simulation, access or even observe the hardware running it? This brings us to the philosophical challenges of the theory, such as questioning the very nature of consciousness and reality itself. While definitive evidence remains elusive, the simulation hypothesis has transcended its origins in science fiction, becoming a central point of discussion in fields like technology, philosophy, and cosmology. In 2012, a monumental discovery at the Large Hadron Collider (LHC) rocked the world of physics: the detection of the Higgs boson. This elusive particle was the final missing piece of the standard model of particle physics, explaining how elementary particles acquire mass. Its discovery holds profound implications not just for particle physics, but for our understanding of the universe's formation. The Higgs boson and its associated field provide the mechanism by which electroweak symmetry was broken shortly after the Big Bang. This event split the electromagnetic and weak nuclear forces, ultimately enabling particles to acquire mass. Without this critical process, atoms could not form, and life as we know it would not exist. The implications of the Higgs field extend far beyond just particle physics. By studying its behavior in the early universe, scientists can better understand the dynamics of cosmic inflation, an era of rapid expansion following the Big Bang. This phase smoothed out the structure of the universe and seeded the fluctuations that eventually became galaxies, stars, and planets. Moreover, the Higgs boson may offer valuable insights into areas beyond the standard model, such as supersymmetry, extra dimensions, and dark matter. These areas attempt to solve some of the most challenging problems in physics, like the hierarchy problem and the unification of forces. Additionally, the precise mass of the Higgs boson has sparked new investigations into the stability of our universe. Its mass lies in a precarious position between a stable universe and one that is potentially unstable. This discovery suggests that the universe may exist in a delicate state, raising the possibility of future vacuum decay. Such findings prompt even more profound questions about the ultimate fate of the universe itself. Will it continue expanding forever, or is there an end to its existence? The Higgs boson's discovery, therefore, is not just a triumph of particle physics. It may hold the key to understanding the long-term stability and future of the cosmos. In conclusion, the Higgs boson represents more than just a cornerstone of particle physics. Its discovery has opened doors to new realms of understanding, from the earliest moments of the universe's creation to its potential end. The questions it raises and the mysteries it illuminates make it one of the most exciting and thought-provoking discoveries in modern science, setting the stage for future research that could shape our understanding of everything, from the infinitesimal to the infinite, but also a key to unlocking the deepest mysteries of the universe. The quest to understand the cosmos, its formation, and the laws governing its vast expanse has captivated humanity for centuries. Central to this exploration is the ultimate pursuit of a unified theory of physics, a theory of everything, TOE. This elusive concept represents the holy grail of theoretical physics, aiming to create a single, all-encompassing framework that can reconcile the wide range of physical phenomena spanning from the quantum to the cosmological scales. A theory of everything seeks to merge the four fundamental forces of nature: strong nuclear force, weak nuclear force, electromagnetism, and gravity, into a cohesive model. Such a theory would offer a seamless explanation for the workings of the universe, answering questions about everything from the subatomic realm to the grand scale of galaxies. Currently, the standard model of particle physics successfully describes three of these forces: strong, weak, and electromagnetic, within the framework of quantum field theory. Yet it falls short of incorporating gravity. On the other hand, general relativity, Albert Einstein's revolutionary theory, beautifully accounts for gravity and the fabric of space-time. However, when it comes to the quantum realm, or the high-energy extremes, it runs into conflicts with quantum mechanics. This incompatibility leaves a major gap in our understanding, highlighting the need for a truly unified theory that bridges quantum mechanics and general relativity, creating a quantum gravity framework capable of working across all scales and energies. One of the leading contenders for such a unified theory is string theory. This theory suggests that the fundamental building blocks of the universe are not zero-dimensional particles, but rather tiny, vibrating strings. These strings vibrate at different frequencies, and their modes of vibration correspond to the various particles and forces that make up the universe. Intriguingly, string theory naturally incorporates gravity, which has been a challenge for other quantum theories, and it even proposes the existence of additional spatial dimensions beyond the familiar three. Alternatively, loop quantum gravity offers another fascinating approach. Instead of relying on extra dimensions, this theory proposes that spacetime itself is quantized. It envisions a universe made up of discrete loops, intricately woven together to form the very fabric of reality. This theory aims to reconcile the geometry of space-time, as described by general relativity, with the principles of quantum mechanics, without invoking the extra dimensions that string theory does. For a unified theory to be successful, it must make precise, testable predictions. This would allow for experiments or observations that could either validate or challenge the theory. Furthermore, it would need to address some of the most pressing mysteries in modern cosmology, including the nature of dark matter and dark energy, the imbalance between matter and antimatter, and the enigmatic behaviors of black holes. Solving these puzzles could reveal new insights into the very nature of the universe. The implications of discovering a theory of everything would be nothing short of monumental. The breakthrough would not only advance our understanding of physics, but also profoundly impact all of science. New technologies and revolutionary methods of interacting with the world could arise from the application of such a theory. Beyond the practical benefits, it would offer a deeper, philosophical understanding of humanity's place in the universe, providing the most fundamental insight into the nature of reality ever achieved. Quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales, may seem at first glance to be entirely separate from the vast cosmic events that shape the universe. Yet, quantum mechanics exerts a profound influence on the structure of the cosmos and the way it operates. At the dawn of the universe, during the Big Bang, the cosmos was incredibly small. Quantum fluctuations, temporary changes in energy at specific points in space, played a crucial role in the evolution of the universe. These quantum fluctuations were magnified during cosmic inflation, a period of exponential expansion in the early universe. This rapid stretching of space could have created slight variations in the density of matter, which later grew into the galaxies and the large-scale structures we see today. Thus, the majestic tapestry of the universe we observe now may have its origins in the quantum fluctuations of the universe's infancy. Moreover, quantum mechanics is essential to understanding the life cycles of stars. The fusion processes that power stars, including our sun, rely on quantum tunneling, an effect that allows particles to pass through energy barriers that classical physics would deem insurmountable. This process enables the nuclear reactions that power stars and produce the heavier elements, which are essential for life and the universe's chemical diversity. Quantum mechanics also plays a key role in the extreme environments around black holes. According to quantum theory, these objects emit Hawking radiation, a process where particle-antiparticle pairs are created near a black hole's event horizon. One particle may fall into the black hole while the other escapes, leading to the gradual evaporation of the black hole over astronomical timescales. This process could fundamentally change our understanding of the life cycles of black holes. In the realm of dark matter and dark energy, two of the biggest mysteries in cosmology, quantum mechanics may offer crucial explanations. For example, axions, hypothetical particles that arise from certain quantum theories, are proposed as possible candidates for dark matter. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, may have roots in quantum field theory. Some theorists suggest that it could be the result of vacuum energy that permeates all of space, further reinforcing the idea that quantum mechanics plays a central role in the most profound cosmic phenomena. In conclusion, the influence of quantum mechanics on cosmic events highlights the deep interconnectedness of the universe. From the tiniest particles to the largest galaxies, quantum mechanics weaves through every layer of existence, enriching our understanding of the cosmos. It not only provides the framework for how individual particles behave, but also sheds light on the grand design of the universe itself. As we continue to search for a unified theory of physics, it is clear that the principles of quantum mechanics will be indispensable in guiding us toward a deeper understanding of the universe's fundamental nature, but also urge us to rethink our understanding of life's resilience in the vast expanse of the cosmos. These organisms, thriving in environments once considered inhospitable, are a reminder of how adaptable life can be, pushing the boundaries of what we thought possible. This newfound perspective challenges us to expand our search for life beyond Earth, no longer limiting it to planets within the so-called habitable zone. With extremophiles, we're forced to reconsider the definition of life itself, no longer confined to Earthly conditions. At the heart of this exploration lies the concept of wormholes, hypothetical passages that could reshape our understanding of space and time. Imagine the possibility of shortcuts through the curvature of space-time, enabling not only faster travel across the universe, but even potentially unlocking the secrets of time travel. Wormholes, theorized through Einstein's general theory of relativity, are bridges connecting distant points in both space and time, potentially allowing for instant travel across vast distances or to points in the past or future. This theory, although captivating, is still rooted in speculative physics, and the feasibility of creating or stabilizing such a passage remains far beyond our technological grasp. The challenges of wormhole travel are immense. Theoretical models suggest that the energy required to stabilize a wormhole would be immense, potentially involving a form of matter that has yet to be discovered or fully understood, referred to as exotic matter. And even if we were able to create these bridges, the risks associated with navigating through them could be catastrophic, as the intense gravitational forces could stretch or destroy anything that attempts to pass through. The hypothetical nature of wormholes continues to fuel scientific inquiry and public imagination, but it's clear that time travel, though a tantalizing prospect, remains far from realization. As we dream of these futuristic possibilities, we are simultaneously confronted with the harsh reality of our current understanding of life's origins. The search for life beyond Earth is guided by fundamental criteria that are based on the very conditions we know to support life here. Liquid water, for instance, is universally acknowledged as essential. It is the solvent that enables the biochemical reactions vital for life, and its presence is considered a non-negotiable requirement for any planet or moon to support life. Similarly, temperature plays a critical role. A planet must be within a certain range, not too hot to boil away the water, nor too cold to freeze it, ensuring the stability of complex molecules essential for life. Further, a stable atmosphere and magnetic field are crucial for shielding life from harmful cosmic and solar radiation. Without them, any form of life would be at the mercy of the radiation that bombards the surface of planets. This protection allows gases like oxygen, carbon dioxide, and nitrogen to remain in the atmosphere, supporting the biological processes that sustain life. These elements are the building blocks of life, the very foundation for molecules like proteins, nucleic acids, and lipids. It's these criteria that guide our search for life beyond Earth, pushing us to explore planets and moons that might harbor life, even in environments that were once thought to be too extreme for survival. Despite these criteria, the discovery of extremophiles has expanded our horizons. These remarkable organisms thrive in environments that defy the expectations of life as we know it. From the searing heat of hydrothermal vents to the freezing cold of deep-sea ice, extremophiles have proven that life can flourish in conditions previously thought to be beyond the realm of possibility. Their discovery has not only revolutionized our understanding of life's adaptability, but has also opened new avenues for the search for extraterrestrial life. Could life be hiding on moons like Europa or Enceladus, where subsurface oceans remain shrouded beneath icy crusts? Or in the dust storms of Mars, where some scientists now speculate microbial life might have once existed, or perhaps still does? The implications of extremophiles extend far beyond Earth. As we look to the stars, their existence suggests that life could potentially exist in the most unexpected corners of the universe. Whether on distant exoplanets orbiting other stars or in the hidden depths of moons in our own solar system, life may be more common than we think. And just as extremophiles have revealed the incredible adaptability of life here on Earth, they inspire a sense of wonder about the limitless possibilities that may await us as we continue to explore the universe. Thus, as we venture into the unknown, we must ask ourselves, what if life exists in forms we cannot yet imagine, in places we once deemed uninhabitable? The search for life beyond Earth is no longer confined to the realms of science fiction. It is an exciting, unfolding chapter in humanity's quest to understand our place in the universe. Each discovery, from the theoretical physics of wormholes to the real-world survival of extremophiles, brings us one step closer to understanding the vast potential of the cosmos. But also, it is essential to explore the biochemical adaptability of life. For example, certain extremophiles, organisms that thrive in harsh conditions, utilize sulfur or methane as an energy source instead of the sunlight that most life on Earth depends on. This remarkable adaptability suggests that alien life forms might not rely on the same metabolic processes we are familiar with, sparking a profound shift in our understanding of what life can be. Extremophiles are not just curiosities. They are revolutionizing the search for extraterrestrial life by broadening the possibilities of where and how life could exist. Their existence insinuates that life might be able to flourish in environments we once thought inhospitable, perhaps even on distant planets or moons far beyond our solar system. As we look up into the vast cosmos, we may be closer than ever to discovering that the universe is far more hospitable to life than we previously imagined. The quest to uncover extraterrestrial intelligence, more commonly known as SETI, Search for Extraterrestrial Intelligence, is an exploratory science aimed at finding signs of life beyond our planet. Through this endeavor, scientists strive to detect some form of technological signal, radio waves, light patterns, or other transmissions that could indicate intelligent life elsewhere in the universe. SETI researchers use highly sensitive telescopes to listen for signals that could not have originated from natural processes, essentially listening for messages from other civilizations. A crucial tool in this search is the radio telescope, a technology capable of detecting the faintest radio waves emitted across the cosmos. These signals, if they exist, could be proof of advanced technological life far beyond our own capabilities. The reason this search is so compelling lies in the nature of electromagnetic waves, like radio waves or light. These waves can travel across vast distances in space without being significantly dispersed or absorbed. This means that if an advanced civilization were attempting to communicate, or even if their technological emissions were leaking into space as byproducts, they could travel far beyond their origin. If such emissions were to reach Earth, SETI scientists could potentially detect them, bringing us one step closer to making contact with intelligent beings from another world. It's this understanding that fuels the drive to continue searching for signals from space, believing that the cosmos might indeed hold civilizations far more advanced than our own. Guiding SETI's search are a number of theoretical and practical frameworks, including the famous Drake equation, developed by astronomer Frank Drake in 1961. This equation seeks to estimate the number of active, communicative extraterrestrial civilizations in our own Milky Way galaxy. While much of the equation involves speculation, it offers a structured approach to pondering the vast factors that play into the existence of extraterrestrial intelligence. Still, SETI encompasses a variety of methods beyond just listening for signals. Some scientists advocate for a more active approach, what is known as MET, or Messaging Extraterrestrial Intelligence. This involves sending messages to stars that may have habitable planets, with the hope of establishing a two-way communication channel. These messages are carefully crafted to share information about our civilization and our location in the universe, in hopes of receiving a response. Despite decades of listening intently for signals and some intriguing but ultimately unrepeatable results like the WOW signal of 1977, SETI has yet to find definitive evidence of extraterrestrial intelligence. However, technological advancements continue to improve our chances. The development of more sophisticated telescopes and our expanding knowledge of the universe make the possibility of contact more plausible than ever before. SETI's search remains one of the most profound and speculative endeavors in human history, symbolizing our deep intrinsic curiosity about our place in the cosmos and the possibilities that lie beyond our home on Earth. One of the most revolutionary discoveries that could reshape our understanding of life in the universe would be the detection of microbial life on Mars. If evidence of microbial life were found, it would mark a watershed moment in human history. For the first time, we would have direct evidence that life is not exclusive to Earth. This would strongly suggest that life could be a common occurrence across the cosmos, present on countless other planets and moons, scattered throughout the universe. Such a discovery would have profound implications not only for biology, but for fields across the scientific spectrum. It would ignite intense research into the biochemistry of Martian life, revolutionizing our approach to the study of life itself. This new understanding could also spark a wave of exploration to other planets in our solar system, as humanity seeks to discover more about the potential for life to thrive beyond Earth. In this monumental quest to understand our place in the universe, the discovery of life, whether microbial or intelligent, would reshape everything we thought we knew about biology, evolution, and the very nature of existence. In a future where the search for extraterrestrial life becomes more than just a speculative endeavor, the discovery of Martian microbes would ignite profound questions about life's origins. Are these microbes related to Earth's life forms, suggesting a panspermia event where life was transferred from one planet to another? Or do they represent an entirely independent genesis of life, suggesting that life can arise in multiple forms under varying conditions? This discovery could fundamentally alter our understanding of biology and the conditions necessary for life to thrive. If life on Mars is independent, it would force scientists to expand the parameters of their search for extraterrestrial life. we would no longer be confined to seeking life only in environments similar to Earth's. This revelation would encourage the exploration of a broader spectrum of habitats, from icy moons to planets with extreme volcanic activity, changing the way we view the potential for life beyond Earth. In essence, it would widen the scope of astrobiology, urging us to explore environments previously thought to be uninhabitable. The validation of Martian life would also set the stage for future missions aimed at studying these Martian life forms in their native environment. As the quest to understand alien biology intensifies, the need for stringent biocontainment measures would become paramount. Both forward and backward contamination between Earth and Mars would need to be strictly controlled, preventing Earth's microbes from interfering with Martian ecosystems and ensuring that Martian life remains free from earthly influences. This focus on biocontainment would add a new layer of completist space exploration, pushing us to consider the ethical and ecological ramifications of our presence on Mars. The discovery of life on Mars would have implications far beyond science. Philosophically, it would challenge humanity's long-held beliefs about our place in the universe. The knowledge that we are not alone could force a collective reconsideration of our significance on a cosmic scale. Religions, philosophies, and societies would grapple with the reality of extraterrestrial life, potentially leading to new interpretations of creation, existence, and the nature of life itself. This shift in perspective could inspire a renewed sense of wonder and humility, encouraging us to think more deeply about our responsibilities as stewards of Earth. On the global stage, the discovery could foster unprecedented cooperation between nations. Countries and private entities would unite in the pursuit of understanding Martian life, leading to joint missions, shared research, and collaborative efforts to explore the Red Planet and beyond. This newfound spirit of international cooperation could redefine space exploration in the 21st century, transforming the race to explore Mars into a collective human endeavor. At the same time, this discovery could ignite a new space race as nations and private companies vie to lead the charge in exploring and studying life on Mars, with the potential to revolutionize industries and technologies that have yet to be imagined. In sum, the discovery of microbial life on Mars would not only mark a scientific revolution, but also reshape our view of existence itself. It would bridge the fields of planetary science and biology, expanding our understanding of life's potential diversity. We would gain insight into how life can adapt to environments vastly different from those found on Earth, challenging our assumptions and broadening the horizons of what we consider possible. The implications for humanity's place in the universe, our scientific approach to life, and the potential for collaboration in space exploration would be profound and far-reaching. Understanding the mechanisms through which life could adapt to alien environments requires a deep dive into biochemistry, evolutionary biology, and the physics of other worlds. On Earth, life has demonstrated an extraordinary ability to adapt to extreme conditions, whether it be deep-sea hydrothermal vents where temperatures and pressures exceed what we once thought was possible for life, or the freezing, dry valleys of Antarctica where water is scarce and conditions are harsh. The adaptability of life on Earth suggests that if life exists elsewhere, it might also exhibit similarly remarkable resilience. In environments where sunlight is limited or absent, life on other planets might find alternative energy sources to sustain itself. For instance, on a planet with frequent volcanic activity, organisms might rely on chemosynthesis, using chemical energy to produce food, just as certain Earth organisms do in deep-sea ecosystems. Similarly, on a world where water is scarce, life might have evolved to extract moisture from the atmosphere or utilize liquid methane or ammonia as solvents, an idea speculated for life on Saturn's moon Titan. The adaptability of life to such extreme conditions suggests that, if Martian life exists, it may have evolved to survive in ways that are completely alien to us. Radiation-resistant organisms could be another example of how life might adapt to a Martian environment. If Mars has a thin atmosphere or weak magnetic field, its surface could be bombarded by cosmic radiation. On Earth, extremophiles, organisms that thrive in extreme environments, show us that life can survive under conditions we once thought inhospitable, including high levels of radiation. The discovery of such organisms on Mars would be a striking testament to the resilience of life, highlighting the potential for life to flourish under radiation-heavy conditions. Similarly, the ability of life to adapt to different temperatures and atmospheric compositions would push the boundaries of what we know about biology. Life forms on Mars might breathe different chemical compounds, such as carbon dioxide or methane, or evolve to thrive in temperatures far colder or hotter than those found on Earth. These adaptations could involve entirely new biochemical processes, such as the use of alternative chemicals for photosynthesis, or entirely different molecular structures for genetic material. This potential for diversity is a reminder that life on Mars, or any other world, could be far more exotic and complex than we can currently imagine. The discovery of life on Mars would thus expand our understanding of life's potential diversity, opening up new possibilities for the existence of life across the cosmos. It would provide strong evidence that just as life on Earth has adapted to nearly every imaginable niche, life elsewhere in the universe could similarly adapt to the unique conditions of its home planet. And as we venture further into space, we will continue to search for these clues that could one day reveal the answer to the ultimate question: are we alone? But also underscores the resilience of life as a universal phenomenon capable of thriving even in the harshest conditions imaginable. The quest to find biosignatures on distant planets presents an intriguing and daunting challenge for astronomers and astrobiologists alike. These biosignatures, which could indicate the presence of life, range from complex organic molecules to atmospheric patterns that suggest biological activity. However, the search is far from straightforward due to the immense distances separating Earth from potentially habitable worlds. Many of these planets are light years away, residing in distant star systems, requiring astronomers to rely on incredibly sensitive instruments to detect the faintest traces of light that pass through their atmospheres or are reflected from their surfaces. One of the most powerful tools in this quest is spectroscopy, a technique that breaks down light into its component spectra, allowing scientists to determine which gases are present in a planet's atmosphere, yet distinguishing between true biosignatures and abiotic signatures, those signals that mimic life but are generated by non-biological processes, remains a significant challenge. Take methane, for example. While it is a known biological marker here on Earth, it can also be produced through geological activity. This makes it impossible to assume that the presence of methane alone unequivocally suggests biological activity. A more comprehensive understanding of the planet's geology and chemistry is essential to interpreting these signals properly. The sensitivity and resolution of current telescopes often limit our ability to gather detailed data from these distant worlds. Although both ground-based and space telescopes are in development, overcoming these technical limitations is no easy feat. Detecting and analyzing faint biosignatures with the required precision remains one of the most significant obstacles. Another layer of complexity is added by the potential diversity of life itself. Our search assumes that extraterrestrial life, if it exists, would produce biosignatures similar to those of life on Earth. However, life on other planets could have evolved along entirely different biochemical pathways, leading to biosignatures that we do not yet recognize as indicative of life. The dynamic nature of planetary atmospheres, including our own, further complicates this search. Seasonal changes, volcanic eruptions, and other natural processes can temporarily alter atmospheric composition, potentially obscuring or even mimicking biosignatures. Despite these numerous challenges, the pursuit of biosignatures remains a key endeavor in answering one of humanity's oldest questions. Are we alone in the universe? Every technological advancement and new methodology brings us one step closer to unraveling this mystery, though we are still far from certain answers. The exploration of icy moons, such as Europa, one of Jupiter's largest moons, involves a multifaceted approach. Scientists are particularly intrigued by the potential for life beneath Europa's thick, icy crust, where a vast, salty ocean is believed to exist. This ocean could provide the right conditions for life to thrive, and remote sensing from telescopes and spacecraft orbiting Jupiter has revealed faint plumes of water vapor erupting from cracks in the ice. These plumes offer indirect clues about the composition of Europa's subsurface ocean and its potential to support life. One of the primary strategies for investigating icy moons like Europa involves the use of spacecraft equipped with advanced instruments capable of performing detailed reconnaissance. NASA's upcoming Europa Clipper mission is set to conduct a series of flybys using radar to penetrate the moon's icy surface and provide insights into the properties of the ocean beneath. Other instruments on board will map surface composition, search for subsurface lakes, and analyze the tenuous atmosphere for possible biosignatures. A more ambitious future mission could involve landing on Europa's surface, taking direct samples of the ice, and potentially drilling or melting through it to access the ocean below. Such a mission could analyze the chemical makeup of Europa's waters, searching for organic molecules or even microbial life. In addition to these specific strategies, the search for life on icy moons like Europa requires an interdisciplinary approach, combining the expertise of geologists, chemists, oceanographers, and astrobiologists. This holistic perspective is crucial for interpreting the data, especially given the possibility that extraterrestrial life might differ fundamentally from life on Earth. By synthesizing data from multiple missions and employing innovative analytical techniques, scientists hope to uncover the mysteries of Europa and other icy moons, potentially making groundbreaking discoveries that reveal the conditions necessary for life beyond our planet. As we continue our search for life, other worlds such as Venus and Titan also beckon. While both offer extreme environments, they pose unique challenges to the possibility of life. Venus, with its thick atmosphere composed mainly of carbon dioxide, scorching temperatures, and clouds of sulfuric acid, seems an unlikely candidate for life as we know it. However, recent observations have hinted at the presence of phosphine gas in Venus's upper atmosphere, a potential biosignature here on Earth. This has sparked renewed speculation about the possibility of microbial life surviving in the more temperate regions of the Venusian atmosphere, where conditions might be less extreme. Life, if present, could potentially exist airborne, thriving within the clouds themselves. In this ongoing quest, each new discovery brings us closer to understanding the true potential for life beyond Earth. While we have yet to find definitive proof of extraterrestrial life, the exploration of other planets and moons continues to challenge our perceptions of what is possible, offering tantalizing glimpses into the potential for life in the farthest reaches of our universe. The exploration of distant worlds like Titan, Saturn's largest moon, brings with it a thrilling blend of possibilities and uncertainties. This intriguing moon presents a unique set of conditions that may hold the key to understanding the adaptability of life beyond Earth. Titan is a world of contradictions, an inhospitable surface of frigid temperatures and a thick, nitrogen-rich atmosphere that is vastly different from what we know on our planet. Its surface temperature averages around 209 degrees Fahrenheit, far colder than Earth's polar regions. Yet beneath these extreme conditions, Titan harbors a vast mystery, a subsurface ocean of liquid water hidden deep beneath the icy crust, which could potentially harbor life. However, without direct evidence, much of this remains speculative. Titan's frigid surface is too cold to support life as we know it. But could life exist in its hidden ocean, shielded from the hostile surface conditions? If life were to thrive there, it would likely need to adapt to incredibly cold and high-pressure environments, possibly using chemical energy derived from hydrothermal vents, similar to how certain extremophiles on Earth survive in the most hostile conditions imaginable. This adaptation to an extreme environment would allow life to flourish without sunlight, relying instead on chemical reactions as its source of energy. Titan's methane cycle, which mirrors Earth's water cycle, further strengthens the intrigue. Just as Earth's water cycle drives weather patterns and supports life, Titan's methane cycle plays a key role in shaping its landscape, with vast lakes and rivers of liquid methane and ethane flowing across its surface. The complex organic chemistry found both in Titan's atmosphere and on its surface presents an unparalleled case study for prebiotic chemistry, offering vital clues about the processes that could lead to the formation of life or its building blocks. This makes Titan an extraordinary natural laboratory for scientists interested in studying life's potential origins. Nonetheless, whether life exists on Titan depends heavily on one fundamental question. Can life adapt to environments that are fundamentally different from those on Earth? This is a question that goes beyond Titan and extends to other celestial bodies like Venus and Mars, where future missions could yield profound insights into the possibilities of extraterrestrial life. As these missions progress, analyzing the atmospheres of Venus or exploring the subsurface ocean of Titan, we may uncover a new understanding of the conditions that could support life, or perhaps the discovery that life, in some form, already exists. But these exciting prospects come with significant ethical dilemmas. The very act of exploring and potentially colonizing other worlds raises the issue of contamination, the introduction of Earth life into environments that may already harbor their own ecosystems. The prospect of polluting other planets or moons with terrestrial microorganisms presents a challenge that intertwines scientific curiosity with ethical responsibility. This issue, which falls under the principles of planetary protection, is centered around preventing the unintended spread of life from Earth to other worlds, as well as preventing contamination from other worlds back to Earth. The ethical concerns are multifaceted. On one hand, introducing Earth-based life forms to places like Mars or Europa could jeopardize future astrobiological studies. If Earth's microbes were to mix with alien life forms, distinguishing between native organisms and contaminants could become impossible, leaving us in a perpetual state of uncertainty about whether extraterrestrial life exists. On the other hand, Earth's life forms might also threaten the natural balance of ecosystems that could exist on other planets, just as invasive species on Earth have disrupted ecosystems here. Earth-based microbes, if introduced, could outcompete native life forms for resources, leading to the potential extinction of these alien organisms. This raises a critical ethical question. Should humanity, in its quest for knowledge, risk destroying ecosystems we have yet to fully understand? The preservation of extraterrestrial ecosystems calls into question our responsibilities as stewards of the universe. Are we simply extending the legacy of colonialism, historically the exploitation of new lands for the resources of space? What rights do we, as inhabitants of Earth, have to assert control over pristine extraterrestrial environments? These questions delve deep into the philosophical and moral dimensions of space exploration. Should we continue to prioritize resource extraction over environmental preservation? Should our scientific curiosity extend to the point of exploitation? Or should we instead embrace a sustainable, respectful approach to exploration? The principles behind these questions are not merely hypothetical. They are woven into the fabric of international space law, most notably the Outer Space Treaty of 1967, which stipulates that space exploration should avoid harmful contamination of celestial bodies. Similarly, the guidelines set forth by the Committee on Space Research, COSPAR, provide a legal framework that aims to mitigate risks of contamination. Yet, as humanity advances toward the possibility of human missions to Mars and beyond, these legal frameworks will need to be continually adapted to ensure that ethical considerations evolve alongside technological progress. In this new era of space exploration, we must balance our thirst for knowledge with a respect for the unknown. Our responsibility is not just to seek answers, but to do so in a way that safeguards the integrity of the environments we explore and preserves the cosmic wilderness for future generations. As we venture deeper into the cosmos, we must ask ourselves, are we exploring space with the humility and care that these celestial bodies deserve? Or are we, in our ambition, simply repeating the mistakes of the past? In the far reaches of our solar system, there exists a mysterious and theoretical structure that has captivated astronomers for decades. This is the Oort cloud, an enigmatic shell of icy bodies, thought to reside far beyond Pluto, in the outermost stretches of the solar system. Named after the Dutch astronomer Jan Oort, who first proposed its existence in 1950, this distant region is believed to be the birthplace of long-period comets, those that take more than years to complete an orbit around the Sun. The Oort cloud is thought to be a vast repository of icy objects, comets, and remnants from the early solar system. These objects are believed to have been ejected from the inner solar system by the gravitational forces of the giant planets, such as Jupiter and Saturn, in the formative stages of our solar system's history. The Oort cloud extends from approximately 2,000 to 100,000 astronomical units, AU, from the Sun. For reference, 1 AU is the distance from Earth to the Sun, about 93 million miles. Given its immense distance, the Oort cloud remains incredibly challenging to study directly, with its existence largely inferred from the behavior of long-period comets and computational models that simulate the solar system's formation. The secrets of the Oort cloud are tantalizing for astronomers. Despite numerous studies, much about this distant region remains shrouded in mystery. For instance, the precise composition and distribution of the objects within the Oort cloud remain unknown, as does how these objects have evolved over time. Some theorists suggest that the Oort cloud could hold essential clues to the early conditions of the solar system, potentially providing insights into how comets are delivered to the inner solar system. These icy wanderers may have played a crucial role in bringing water and organic molecules to Earth, possibly contributing to the development of life as we know it. Moreover, external forces may play a pivotal role in shaping the behavior of the objects within the Oort cloud. Stars passing near our solar system, the tidal effects of the Milky Way, and even the mysterious influence of dark matter could perturb the orbits of Oort cloud objects. These interactions might send some of them hurtling toward the inner solar system, potentially triggering long-period comets. Understanding these dynamics could offer profound insights into the behavior of our solar system and its position within the broader context of the Milky Way. The Oort cloud might also not be unique to our solar system. It is likely that other stars have their own versions of this distant cometary. Studying these clouds could shed light on the formation of planetary systems across the galaxy, offering valuable comparisons to our own solar system's evolution. By unlocking the mysteries of the Oort cloud, we can not only deepen our understanding of our solar system's history, but also gain insight into the formation and evolution of planetary systems in other parts of the universe. Equally captivating are the nebulae that dot the cosmos, vast, luminous clouds that are the birthplaces of stars and planetary systems. Nebulae are formed through a variety of astronomical phenomena, each contributing to the stunning variety seen across the universe. Some nebulae arise from the death throes of stars, while others form as regions of dense gas and dust collapse to create new stars. The diversity of nebulae in the universe reflects the different processes that lead to their creation, offering a window into the life cycle of stars and the conditions in which new ones are born. One of the most common ways nebulae form is through the death of stars, particularly those with masses comparable to or greater than our Sun. As these stars near the end of their life, they undergo dramatic transformations. For stars of low to medium mass, this often involves expanding into a red giant before shedding their outer layers into space. The expelled material forms what is known as a planetary nebula, which glows brightly as it is ionized by the hot core left behind, a white dwarf. For more massive stars, their demise is marked by a cataclysmic supernova explosion. The explosion ejects the star's outer layers into space, leaving behind a supernova remnant nebula. A striking example is the Crab Nebula, which resulted from a supernova explosion observed in 1054, serving as a vivid reminder of the violent end of stars. In addition to these stellar deaths, nebulae can form as new stars are born within giant molecular clouds, vast regions of gas and dust. Gravitational forces cause certain regions of the cloud to collapse, leading to the formation of new stars. This process gives rise to emission nebula, which glow in a spectrum of colors depending on the elements present, most commonly hydrogen, which emits a red hue. The Orion Nebula, often called a stellar nursery, is one of the best-known examples where young stars illuminate the surrounding gas and dust, giving the nebula its characteristic glow. Nebulae can also form through the scattering of starlight by dust in regions of space, giving rise to reflection nebula. Unlike emission nebula, the gas in reflection nebulae is not ionized. Instead, these nebulae shine by reflected light from nearby stars. The Pleiades star cluster, surrounded by a beautiful reflection nebula, is a perfect example of this interaction, where starlight reflects off the dust, creating a stunning cosmic image. In both the Oort cloud and nebulae, the cosmos reveals its deepest secrets. mysterious, captivating, and full of potential for discovery. These regions are not only critical to understanding the formation of our solar system, but also offer a glimpse into the universal processes that shape stars, planets, and the galaxies in which they reside. As we continue to explore these far reaches, we find ourselves unraveling the mysteries of the universe, one discovery at a time. Dark nebula, such as the Horsehead Nebula, emerge from the vast expanses of space as stunning silhouettes against the brighter backgrounds of distant stars or emission nebula. These regions, dense with clouds of dust and gas, obscure the light from background stars, creating striking figures against the cosmic backdrop. The formation of these nebulae, regardless of their type, marks a pivotal phase in the life cycle of stellar evolution. It is here that the processes of creation and destruction unfold in a cosmic ballet, shaping the fabric of our universe. These celestial phenomena are more than just breathtaking sights. They play a vital role in the cosmic cycles that distribute elements across space, seeding the cosmos with the building blocks necessary for future generations of stars and planetary systems. The creation of a nebula is not merely a visual event. It is a fundamental stage in the birth of stars, serving as both a cradle and a forge for the very elements that will go on to form the planets, moons, and other bodies in the universe. Every nebula is a story in itself, a testament to the ongoing dance of birth and rebirth that powers the cosmos. Beyond the enigmatic beauty of nebulae lies a region of our own solar system, the Kuiper Belt, a vast, icy expanse extending beyond Neptune's orbit. Populated with frozen bodies, dwarf planets, and icy remnants of the solar system's early formation, the Kuiper Belt holds key insights into the origins of our celestial neighborhood. This area, often referred to as a treasure trove of ancient material, preserves remnants from the formation of the solar system over 4.6 billion years ago. In many ways, the Kuiper Belt is a window into the processes that shape not only our solar system, but also the broader universe. The Kuiper Belt plays a crucial role in understanding solar system formation. It serves as a repository of primordial debris containing objects that have remained relatively unchanged since the solar system's birth. These bodies, ranging from comets to planetesimals and dwarf planets like Pluto, are composed of a unique mixture of ice and rock materials, remnants of the icy outer regions of the presolar nebula. Studying these objects offers astronomers a glimpse into the chemical composition and physical conditions of the early solar system. They are like fossils, preserving information about the forces that shape the formation of planets, moons, and other celestial bodies. In addition to its role as a record of early solar system history, the Kuiper Belt also provides key evidence for understanding planetary migration. Observations of Kuiper Belt objects, KBOs, and their orbits have contributed to the development of the NICE model, which suggests that the giant planets of the solar system migrated outward and inward before settling into their current positions. This dramatic migration would have profoundly reshaped the solar system, influencing the distribution of Kuiper Belt objects and possibly triggering events like the Late Heavy Bombardment, an intense period of asteroid and comet impacts that dramatically altered the inner solar system. The Kuiper Belt's structure and dynamics continue to offer insight into the gravitational forces that shape our solar system. The presence of objects in orbital resonance with Neptune, for example, highlights the ongoing influence of planetary gravity on distant bodies. Furthermore, the apparent edge of the Kuiper Belt, around 50 astronomical units from the Sun, raises intriguing questions. What limits the Kuiper Belt's extent? Could there be unseen, distant objects lurking beyond, influencing the orbits of KBOs? Some scientists speculate about the existence of a hypothetical ninth planet, which could be exerting its gravitational influence on the outer reaches of the solar system. In studying the Kuiper Belt, astronomers are not only unlocking the history of our own solar system, but they are also gaining insights into the broader processes that shape planetary systems around other stars. The processes observed in the Kuiper Belt, including planetesimal formation and planetary migration, are likely to be common features of planetary system evolution throughout the galaxy. This makes the Kuiper Belt an invaluable case study for comparative planetology, the science of comparing planetary systems across the cosmos, and it may provide crucial clues in the search for life beyond Earth. As we venture further into depths of the solar system, we encounter another fascinating relic from its formation: comets. Often described as dirty snowballs or icy dirt balls, comets are remnants of the early solar system, composed of a mixture of ice, rock, and organic compounds. These ancient celestial bodies reside primarily in the Oort cloud and the Kuiper belt, where they follow highly elliptical orbits that sometimes bring them into the inner solar system. It is here, as they approach the sun, that comets put on a spectacular show. Their icy cores vaporize, creating glowing comas and tails that light up the night sky. But comets are more than just beautiful spectacles. They are among the most pristine objects in the solar system, preserving clues to its early conditions. Because they have remained largely unchanged since the solar system's formation, comets offer scientists a rare and invaluable opportunity to study the materials that existed in the early solar nebula, the same materials that eventually formed the planets and other bodies in the solar system. By analyzing the composition and trajectories of comets, astronomers can unravel the mysteries of the solar system's origins, shedding light on the processes that gave rise to the planets, moons, and perhaps even life itself. In essence, the study of nebulae, the Kuiper belt, and comets opens a window to the distant past, offering insights into the forces that shaped our solar system and the broader universe. These celestial phenomena are not just objects of wonder. They are key players in the ongoing story of the cosmos, shaping the very elements of life and forging the pathways for the future of our solar system and beyond. The exploration of these cosmic relics allows us to peer into the past, understand the present, and perhaps glimpse the future of our place in the universe. Since their formation over 4.6 billion years ago, comets have been regarded as cosmic time capsules, preserving the primordial materials from which our solar system was born. These ancient objects, composed of ice, dust, and gases, carry within them the secrets of the early solar nebula, the vast cloud of gas and dust that collapsed under gravity to form the sun, planets, and everything else in our system. As a comet approaches the sun, its icy nucleus begins to heat up, causing its volatile components to sublimate. This process releases gas and dust into space, forming a glowing coma around the nucleus, and sometimes a distinct tail. These dramatic outbursts are not just stunning to observe, they offer a wealth of scientific information. Through the study of the coma and tail, scientists can analyze the specific elements and compounds present in the comet. This spectroscopic analysis provides critical insights into the chemical makeup of the early solar system, helping to reconstruct the conditions and processes that were active in its infancy. Among the most fascinating discoveries are the traces of water and organic compounds found in some comets, including amino acids. This evidence holds profound implications for understanding the origins of life on Earth. The possibility that comets may have played a role in delivering water and essential organic materials to the early Earth offers a tantalizing clue to the mystery of life's beginnings. These findings also reinforce the idea that the building blocks of life may be widespread throughout the cosmos, potentially offering clues about life on other planets. Furthermore, the orbits of comets, shaped by gravitational interactions with the giant planets, provide valuable evidence supporting the theory of planetary migration. Understanding how these orbits evolve helps astronomers piece together the history of the solar system, shedding light on how the planets and other bodies arrived at their current positions. Recent space missions, such as ESA's Rosetta mission to Comet 67P Churyumov-Gerasimenko, have revolutionized our understanding of comets. Rosetta's close-up observations provided unprecedented details, including the discovery of molecular oxygen and nitrogen in the comet's coma. These findings challenge and refine existing models of solar system formation, offering a deeper understanding of the chemical evolution that shaped the early solar system. In summary, comets serve as windows into the distant past, providing crucial clues about the composition, conditions, and processes that prevailed in the early solar system. Their study not only enriches our knowledge of our own cosmic origins, but also helps place our solar system within the broader context of planetary system formation across the universe. Fast radio bursts, FRBs, are one of astronomy's most enigmatic phenomena. Discovered in 2007, these brief but incredibly intense bursts of radio waves originate from deep space. Despite lasting only a few milliseconds, FRBs release as much energy as the sun produces in nearly an entire day. The immense energy of these bursts, combined with their fleeting nature, has made them one of the most puzzling objects in modern astrophysics. FRBs exhibit a telltale dispersion signal, a pattern that indicates the burst has traveled across vast expanses of space, passing through interstellar and intergalactic media that stretch and scatter the radio waves. This dispersion suggests that FRBs come from sources billions of light years away, far beyond our own galaxy, the Milky Way. Yet, despite extensive research, the exact origins of these bursts remain elusive, sparking heated debates within the scientific community. Initially, all detected FRBs were one-off events, adding to the mystery. However, recent observations have revealed repeating bursts from the same sources, suggesting that some FRBs recurring origins. Theories range from the collapse of massive stars to interactions within dense neutron stars, or even the possibility of alien technology. As astronomers continue to probe the depths of space, the search for answers to the origins of FRBs is far from over. These mysterious signals could hold the key to unraveling new, unexpected aspects of the universe. The study of both comets and FRBs underscores the vast, unexplored frontiers of our universe. While comets reveal the ancient history of our solar system, FRBs push the boundaries of our understanding of distant cosmic phenomena. Together, they represent the incredible diversity of objects and events that define the universe we live in. But in 2016, a breakthrough discovery by astronomers changed our understanding of fast radio bursts, FRBs. They identified a repeating FRB, which indicated that multiple bursts were coming from the same location. This was a pivotal moment as it suggested the existence of different types or sources of these enigmatic bursts. It opened the door for more targeted observational strategies to trace their origins. The discovery quickly sparked a flurry of speculation about what could be causing these bursts. Several possible sources were proposed: highly magnetized neutron stars, known as magnetars, binary star mergers, and even more exotic phenomena like cosmic strings. As the years went by, further observations began to closely link at least some of these bursts to magnetars within our galaxy, providing more evidence to support the idea that these highly magnetic remnants of supernova explosions might be the source of FRBs, or at least one type of them. The process of detecting and studying these bursts involves global collaboration with networks of radio telescopes positioned all over the world. These instruments work in unison to monitor the sky continuously, hoping to catch these fleeting, unpredictable bursts in action. The transient nature of FRBs makes them difficult to study, which is why wide-field radio surveys capable of capturing vast sections of the sky at once are essential. Only through these massive collaborative efforts can scientists hope to uncover the mysteries of FRBs. Understanding FRBs, however, is not just an intellectual pursuit for astronomers. It's a venture that could unlock incredible insights about the universe. The interaction of these bursts with interstellar and intergalactic matter offers a powerful tool for studying the large-scale structure of the cosmos. In fact, these bursts could serve as probes to explore the very fabric of space-time, providing valuable data about the evolution of the universe and the distribution of matter across incomprehensible distances. Venturing billions of light years into the cosmos, astronomers have pushed the limits of modern technology to observe the most distant object known to humanity, a galaxy named GNZ11. This extraordinary galaxy is located a staggering 13.4 billion light-years away, which means we are seeing it as it existed just 400 million years after the Big Bang. When you think about such immense distances, they stop being simple measurements and transform into storytellers, recounting tales of the universe's infancy. The discovery of GNZ11 was made possible through the combined efforts of the Hubble Space Telescope and the technique of spectroscopic redshift. This innovative approach allowed scientists to peer back in time, almost to the very dawn of galaxies themselves. This remarkable observation doesn't just serve as a record for distance, it reshapes our understanding of the universe's early days. It provides vital insights into galaxy formation and the rate of cosmic expansion. For astronomy enthusiasts and experts alike, the fact that we are able to study GNZ11 is nothing short of awe-inspiring. We are witnessing the youthful glow of a galaxy evolving in a universe that was much younger than the one we know today. Gamma-ray bursts, GRBs, represent some of the most intense and energetic events in the cosmos. They are so powerful that for a brief moment, they outshine entire galaxies. GRBs come in two main forms: short-duration bursts, lasting less than 2 seconds, which are believed to result from the merger of neutron stars, and long-duration bursts, which last more than 2 seconds, often linked to the supernova explosions of massive stars. These colossal events release an enormous amount of gamma rays, the highest energy form of light. The radiation from these bursts travels across the universe until it reaches Earth, where it is detected by satellites and observatories designed to capture gamma-ray frequencies. The study of GRBs has revolutionized our understanding of the universe in several profound ways. They act as cosmic beacons, illuminating the farthest and most ancient corners of the cosmos, thus providing crucial insights into the early conditions of the universe, just moments after the Big Bang. Additionally, by observing the afterglow of GRBs, astronomers can gather essential data on the rate at which the universe is expanding and how it has evolved over time. But the value of studying GRBs goes beyond merely understanding the expansion of the universe. The extreme environments created by these bursts offer scientists a unique opportunity to test the laws of physics under conditions that are impossible to replicate on Earth. These observations provide critical clues about the behavior of matter and energy at the very edge of our understanding. Through the lens of gamma-ray bursts, we are not just learning about the dramatic events that shape our universe, we are also uncovering the fundamental truths about the nature of the cosmos itself, but also about the fundamental properties that govern the cosmos itself. Magnetars, a rare type of neutron star with an incredibly powerful magnetic field, serve as cosmic laboratories for exploring the mysteries of the universe's magnetic forces. These celestial bodies possess magnetic fields 1,000 times stronger than those of ordinary neutron stars, making them the most magnetic objects known in the universe. Their magnetic fields are so intense that they can rip apart atoms and warp the empty space around them. Understanding magnetars is crucial for astronomers and physicists, as they provide valuable insights into the behavior of matter under extreme magnetic conditions, conditions that cannot be replicated on Earth. The significance of magnetars extends beyond their puzzling features. They also play a pivotal role in the study of cosmic magnetic fields. Observations of magnetars help scientists unravel the processes that amplify magnetic fields in astronomical objects, offering clues about the magnetic properties of various cosmic environments, from stars to galaxies. Magnetars may even hold the key to some of the most mysterious phenomena in the universe, such as fast radio bursts and gamma-ray bursts, linking them to fundamental questions about the universe's structure and evolution. By piecing together the puzzle of magnetars, researchers aim to unlock broader secrets of the cosmos, including the origins of magnetic fields and how they influence the development of the universe. But there's more. Rogue stars, also known as intergalactic or runaway stars, embark on solitary journeys across the cosmos after being ejected from their home galaxies. This grand escape usually begins with dramatic celestial events that serve as cosmic slingshots. In binary star systems, if one star goes supernova, the explosion can propel the surviving companion star at speeds fast enough to escape the galaxy's gravitational pull. Alternatively, close encounters within densely populated star clusters can result in gravitational interactions that fling one or more stars outwards at incredible velocities, sending them hurtling into the vast intergalactic space. The study of rogue stars is not just a tale of cosmic escape artistry, but holds deeper significance for unraveling the mysteries of the universe. Observing these stars as they travel through the voids between galaxies can provide unique insights into the nature of gravitational interactions at both galactic and intergalactic scales. Additionally, rogue stars can act as probes, shedding light on the properties of intergalactic space, a realm that remains largely unexplored due to its diffuse nature. These intrepid stars, in their silent voyage through the darkness, challenge our understanding of the forces that bind galaxies together and the fates that await celestial bodies wandering the cosmic ocean. White dwarfs, on the other hand, are the dense, cooling remnants of stars that have exhausted their nuclear fuel and shed their outer layers. These stellar remnants are incredibly dense. A white dwarf's mass is comparable to that of the Sun, while its volume is similar to that of Earth. This high density arises because the atoms within a white dwarf are squeezed together so tightly that the electrons are stripped from their nuclei, forming a state of matter known as electron-degenerate matter. White dwarfs emit no new light or heat, offering an eerie yet fascinating glimpse into the final stages of a star's life. The study of white dwarfs provides critical insights into the end of stellar evolution, the behavior of matter under extreme pressure, and the nature of the universe's most enduring relics. But glow due to the residual thermal energy from their previous stellar lives, white dwarfs gradually fade away over billions of years. These celestial remnants are not only a fascinating glimpse into the end stages of stars, but also hold the key to understanding the life cycle of stars, including the future of our very own sun. In approximately 5 billion years, our sun will exhaust its nuclear fuel, expand into a red giant, and ultimately shed its outer layers, leaving behind a white dwarf. By examining the properties of white dwarfs, astronomers are able to predict the future characteristics of the sun, its temperature, luminosity, and size in its final stages. Furthermore, white dwarfs serve as cosmic chronometers, allowing scientists to determine the ages of surrounding star clusters in our galaxy. Observing these cosmic embers offers us more than just a window into the fate of stars. It deepens our understanding of stellar evolution and the dynamic, ever-changing cycle of the universe. The Drake equation, formulated by astronomer Frank Drake in 1961, is a thought-provoking probabilistic formula that attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. This equation takes into account various crucial variables, such as the rate of star formation, the fraction of stars that have planets, and the number of planets capable of supporting life. Additionally, it explores the likelihood of life developing on these planets, the emergence of intelligent life, the ability of civilizations to communicate, and the longevity of such civilizations. However, the Drake equation doesn't offer a definitive answer. Instead, it lays out a framework to consider the numerous factors involved in estimating the potential number of extraterrestrial civilizations. Its true significance lies in its transformation of speculation about alien life into a tangible, quantitative inquiry. It stimulates scientific discussion on extraterrestrial intelligence and fuels empirical research in fields like astrobiology and the search for extraterrestrial intelligence. SETI. By analyzing each factor, scientists can systematically assess the chances of contacting alien civilizations. Though certain variables remain impossible to ascertain with certainty, the equation encourages further data collection and theoretical development in planetary systems, the origins of life, and the evolution of intelligence. The Drake equation thus acts as both a speculative tool and a roadmap, guiding research into one of humanity's most profound questions. Are we alone in the universe? Life on Earth is carbon-based, with carbon atoms forming the backbone of all known life forms. This choice of element is due to carbon's exceptional ability to create stable, complex molecules with other elements. However, the vastness of the universe opens up the possibility of alternative biochemistries. Could there be non-carbon-based life forms? If they exist, they would likely be radically different from the life forms we are familiar with, both in their internal chemistry and in their physical appearance. One intriguing possibility is silicon-based life. Silicon, which shares a position directly below carbon in the periodic table, shares some chemical properties with carbon. Yet, silicon bonds are less stable and versatile than carbons, suggesting that silicon-based life, if possible, might only exist under extreme conditions such as high temperatures or pressures where silicon chemistry could be more favorable. These potential life forms might metabolize, reproduce, and evolve in ways that are radically different from carbon-based life, perhaps even utilizing materials like metals or gases that are toxic to us. Exploring the idea of non-carbon-based life forms pushes the boundaries of our understanding of life itself and challenges our Earth-centric definitions. It expands the search for extraterrestrial life by considering a broader array of biochemistries, broadening our perspective on the possible conditions under which life might arise. These theories suggest that life may not be confined to a carbon-based blueprint, but could thrive in the farthest reaches of the cosmos. The Fermi paradox, named after physicist Enrico Fermi, poses a profound contradiction. If the universe is so vast and teeming with stars, planets, and the potential for life, why have we found no evidence of extraterrestrial civilizations? This paradox has sparked numerous hypotheses attempting to explain the apparent silence of the cosmos, despite the high likelihood of other intelligent beings existing. One possible explanation is the rare Earth hypothesis, which suggests that while simple life may be widespread, the conditions necessary for complex life are so rare that Earth becomes an exceptional case. Another theory is the Great Silence, which posits that advanced civilizations might intentionally avoid contact, either for self-preservation or because they have evolved beyond traditional forms of communication. The transcendence hypothesis suggests that advanced civilizations could transcend to higher states of existence, possibly in dimensions or realms that are beyond human comprehension, thus making them undetectable. Another possibility is technological limitations. Our current technology might not be advanced enough to detect alien signals or even recognize evidence of extraterrestrial life. Lastly, the zoo hypothesis suggests that extraterrestrial civilizations are aware of us, but are deliberately avoiding contact, much like zookeepers observing animals in a cage. These theories represent just a few of the many possible explanations for the paradox. Yet, despite the lack of concrete evidence, the search for extraterrestrial life continues to be one of the most profound and exciting pursuits in modern science. But have agreed to not interfere or make contact, treating Earth as a kind of wildlife preserve. In this scenario, 6 temporal displacement civilizations may rise and fall or evolve beyond recognition in such a way that their paths never cross in a manner that would lead to detection or contact. This raises profound questions about our existence, about the very nature of life, intelligence, and the future of humanity. The Fermi paradox remains a cornerstone in the exploration of these questions, encouraging astrobiologists and philosophers alike to dig deeper into the mystery of extraterrestrial life. It drives a multidisciplinary approach to understanding the vast silent complexities of our universe. The concept of the Galactic Habitable Zone, GHZ, helps frame the potential for life beyond Earth. It refers to regions within a galaxy that are most likely to support life as we know it. This is determined by factors such as the right distance from the galactic center, which allows for a safe exposure to radiation, and the presence of stars that possess stable planetary systems, rich in the essential elements needed for life. The GHZ, therefore, offers the optimal conditions for life to evolve and thrive, especially complex life, potentially even advanced civilizations. Life within the GHZ, however, depends on a number of key assumptions. Chief among them is the idea that carbon-based life is universal, and that water remains the essential solvent for life processes. Furthermore, these areas of the galaxy must offer stability for life to evolve from simple organisms into more complex forms capable of developing technological societies. If these assumptions hold true across the galaxy, then regions within the GHZ could be teeming with life, including civilizations that have surpassed humanity in technological achievement and social organization. The search for such civilizations is primarily focused on the detection of exoplanets located within the habitable zones of their stars. Space missions like Kepler and TESS have led the charge in this effort, uncovering thousands of potential candidates. Additionally, projects under the umbrella of the Search for Extraterrestrial Intelligence, SETI, focus on detecting signals from technologically advanced civilizations, signals that may hint at their existence. While no definitive evidence has yet been found, the GHZ remains a promising region of the universe to investigate further. The immense scale and diversity of the Milky Way suggest that, if the conditions are right, advanced civilizations could exist within the GHZ, exploring the cosmos just as we are striving to do now. On a grander scale, the Kardashev scale offers a framework to assess a civilization's level of technological advancement based on its energy consumption. This scale categorizes civilizations into 3 types: Type 1, Type 2, and Type 3, each representing a significant leap in technological capabilities and energy management. A Type 1 civilization, also known as a planetary civilization, would have mastered the ability to harness and store all of the energy available on its planet. Signs of such a civilization would include advanced methods of renewable energy harvesting, solar, wind, and hydroelectric power at a global scale, and the potential to control weather patterns to optimize agricultural output. Natural disasters might be mitigated through technology, and global communication would be seamless. A Type 2 civilization, or stellar civilization, could harness the total energy of its parent star. The most often cited method for achieving this is through the construction of a Dyson sphere, a vast structure or series of satellites built around a star to capture its entire energy output. Technological signs of a Type 2 civilization might include massive space-based structures like Dyson swarms, or stellar engines capable of manipulating a star's motion. A civilization at this level might even be able to control solar phenomena, such as initiating or preventing solar flares. The highest level of the Kardashev scale is Type 3, the galactic civilization. A civilization at this stage would be capable of harnessing and controlling energy on a galactic scale. The technological signs of such a civilization would be almost unimaginable to us, involving the manipulation of entire star systems and the ability to influence the very fabric of space-time itself. With the control of energy across multiple star systems, this civilization could have spread across the entire galaxy, altering the course of cosmic events at will. Such civilizations, if they exist, would be so far beyond our current capabilities that understanding their technology may be as incomprehensible to us as our own advances would be to a pre-industrial society. This staggering scale of technological achievement prompts us to question not only what humanity might one day achieve, but also what secrets the cosmos might still hold, waiting for us to uncover. But imagine this: the manipulation of black holes, the colonization of vast regions of the galaxy, and interconnected communication and transport networks spanning light years. What if we could even harness dark energy or engineer entire star systems? Detecting these signs of advanced alien civilizations might come in many forms: unexpected energy surges across astronomical distances, or patterns of light and radio emissions that don't match any known natural phenomena. We might even observe colossal megastructures, their sheer scale reshaping local space and time. The challenge? Making contact. The vast distances between star systems and the uncertainty surrounding alien language, cognition, and technology complicate the process. Still, researchers have explored potential methods for establishing communication, primarily through mediums that any intelligent civilization might grasp. Take, for instance, the idea of using radio waves, traveling at the speed of light and cutting across the universe with minimal signal degradation. These waves, carrying simple yet profound messages, could bridge light years of space. The foundation of these messages would likely be universal concepts: mathematics, physics, logic, something that transcends cultural or planetary barriers. We could start with prime numbers, the basics of physics, or perhaps even binary code. These are not just abstract ideas, but the fundamental language of the universe itself. A brilliant example of this method in action is the Arecibo message from 1974, a binary encoded transmission that aimed to communicate with extraterrestrial intelligence. It included vital details about human DNA, our solar system, and fundamental math and physics, ideas so universal that any sufficiently advanced civilization should, in theory, understand them. But receiving such a message is just the beginning. Decoding it would present its own unique set of challenges. There would need to be a global effort, uniting humanity, to interpret the message without assuming that the sender thinks like us. The alien civilization could have an entirely different cognitive structure or use communication methods far beyond our current understanding. And so identifying the signal as artificial is only the first step. From there, scientists would need to detect patterns, repetitions, and hidden meanings, anything suggesting the presence of intentional communication. The true breakthrough might come when we establish mutual understanding, when we bridge the gap between human knowledge and extraterrestrial technology, all built on a foundation of shared, universal concepts. The effort might span decades, centuries, or even longer, requiring patience, resilience, and an unwavering commitment to peaceful dialogue. And then there's the concept of Dyson spheres. First conceived by physicist Freeman Dyson in 1960, these hypothetical megastructures represent one of the most fascinating possibilities for an advanced civilization. Dyson imagined vast rings, satellites, or even shells built around stars to capture their entire energy output. This idea was not just speculative, it was practical, a solution to the energy needs of a Type II civilization on the Kardashev scale, one capable of harnessing the full energy of its star to fuel technological expansion. A Dyson sphere, if ever observed, would be a profound indication of an intelligent species. Constructing such a monument would demand not just mind-boggling levels of technology, but also the ability to manipulate entire star systems. The engineering required would be beyond our comprehension. Yet, the mere possibility of such a structure stirs the imagination, hinting at civilizations that have far surpassed our own technological limits. Could such structures exist? What would they look like? And if we find one, what kind of knowledge or communication might they hold? But also, a highly cooperative and purposeful civilization. The engineering challenges alone, materials capable of withstanding close proximity to a star, stable orbital mechanics to prevent collapse or drift, and efficient energy transfer systems suggest a level of technological sophistication far beyond current human capabilities. Astronomers hypothesize that the search for Dyson spheres could be conducted by observing unusual energy signatures in the cosmos. A star encased in a Dyson sphere might emit distinct infrared signatures as the structure absorbs the star's energy and radiates it at lower temperatures. Monitoring stars that unexpectedly dim without typical explanations like an eclipsing companion or stellar variability could also suggest the presence of a structure like a Dyson sphere, partially obstructing the star's light. While no evidence of Dyson spheres has been detected, their potential existence galvanizes the search for extraterrestrial intelligence. This fuels the expansion of our imaginations, pushing the boundaries of how we conceptualize alien civilizations and the technological marvels they might create. Dyson spheres stand as a theoretical testament to what profoundly advanced societies might achieve. They serve as beacons for SETI, Search for Extraterrestrial Intelligence researchers, scanning the galaxy for signs of life beyond Earth. Interstellar travel, a concept that remains firmly in the realm of science fiction for humanity, might conceivably be within reach of advanced alien civilizations. The theoretical strategies proposed for such monumental voyages rely on overcoming the vast distances between stars and the speed of light limitations. These strategies blend our current understanding of physics with imaginative extrapolations of future technologies. One proposed method is the generation ship, a spacecraft designed to support multiple generations of inhabitants during a voyage that could last hundreds or even thousands of years. Such a ship would need to be a self-sustaining biosphere, capable of providing life support indefinitely. Another intriguing concept is suspended animation, or cryosleep, where travelers are put into a state of deep hibernation, significantly slowing biological processes and reducing the need for resources during the journey. This strategy would allow the original crew to survive the long trip without aging significantly. Warp drive technology, a more speculative idea, is grounded in the concept of bending or warping spacetime to allow a spacecraft to travel faster than light, effectively shortening the distance between the origin and destination. While purely theoretical and reliant on exotic forms of matter that may not exist, it is a staple of thought experiments about interstellar travel. The wormhole bridge concept postulates the existence or construction of wormholes, shortcuts through space-time that connect distant parts of the universe. If navigable wormholes could be discovered, created, and stabilized, they could allow near instantaneous travel across galactic distances. However, like warp drive, the science behind wormholes remains highly speculative. Finally, laser or light sail propulsion represents a more grounded approach, utilizing powerful ground or space-based lasers to push a spacecraft with a massive, highly reflective sail. The constant light pressure accelerates the craft to a significant fraction of the speed of light. This method, while still requiring immense technological advancements, is rooted in physics principles we understand today. Each of these strategies embodies the immense challenges and boundless imagination involved in contemplating interstellar travel. For an advanced alien civilization, employing one or a combination of these methods could theoretically make the journey between the stars feasible, presenting a fascinating field of speculation for scientists and science fiction enthusiasts alike. The concepts of panspermia and directed panspermia present intriguing possibilities that challenge traditional views on the origin of life on Earth, stretching our understanding of life's beginnings beyond our own planet, and possibly even beyond our solar system. Panspermia posits that life exists throughout the universe and is distributed by space dust, meteoroids, asteroids, comets, planetoids, or potentially even by spacecraft in the form of unintended contamination by microorganisms. Directed panspermia goes a step further, suggesting that life on Earth might have been seeded deliberately by an advanced extraterrestrial civilization. This theory, if proven, could radically shift our understanding of life and its origins, offering profound implications not just for the Earth, but for the potential for life elsewhere in the universe. The notion that life on Earth originated through abiotic processes, leading to the formation of the first simple biological entities, has long dominated scientific thought. However, a fascinating alternative has emerged in the form of panspermia and directed panspermia. These hypotheses challenge the conventional view, suggesting that life, or at least the fundamental building blocks of life, may not have arisen independently on our planet. Instead, they propose that the essential ingredients for life could have originated in the vast expanse of space, arriving on Earth through cosmic transport, thus sparking the evolutionary processes that eventually led to the rich diversity of life we know today. This radical perspective invites us to reconsider what we believe about the origins of life, both here on Earth and in the universe at large. If panspermia or directed panspermia were to be proven true, it would fundamentally alter our understanding of life's nature and its distribution across the cosmos. Such a revelation would challenge the long-held assumption that life is a rare, earth-bound phenomenon. Instead, it would suggest that life, or at least its essential building blocks, could be a far more common occurrence throughout the universe, perhaps even pervasive across distant galaxies. The implications of this shift in perspective are immense. Should we find evidence supporting the idea that life or its precursors exist beyond Earth, the focus of scientific inquiry would broaden dramatically. It would shift from searching for life in environments that closely mimic Earth's conditions to exploring the most extreme and inhospitable environments the universe has to offer. The scope of our cosmic search would widen, embracing the possibility that life may flourish in unexpected corners of the universe in forms and conditions we've yet to imagine. Moreover, directed panspermia, the idea that intelligent civilizations might intentionally spread life across the universe, opens up profound ethical and philosophical questions. If there are advanced civilizations capable of seeding life elsewhere, what motivates them? Are they driven by altruism, curiosity, or perhaps an entirely different set of values we cannot yet comprehend? This notion forces us to confront deep, unsettling questions about our own existence. Are we alone in the cosmos? Or are we part of a much larger interconnected web of life that spans the galaxies? The very fabric of our philosophical, ethical, and cultural paradigms would be challenged. Beyond these scientific and philosophical considerations, the potential for encountering extraterrestrial life also raises significant ethical dilemmas. If we were to make contact with alien civilizations, we would face a host of challenges that stretch across an array of concerns, from safeguarding humanity and our planet's biosphere to preserving the integrity and autonomy of extraterrestrial civilizations. The unpredictability of such a momentous encounter means that the stakes are impossibly high. The consequences for both humanity and any alien societies we might encounter could be catastrophic or profoundly transformative. One of the foremost ethical concerns in such a scenario is the risk of biological contamination. Imagine the catastrophic consequences of cross-contamination. Introducing microorganisms to an alien world, or vice versa, could lead to the spread of diseases for which neither side has immunity. Invasive species could also disrupt delicate ecological balances, just as species introduced by humans to new environments on Earth have wreaked havoc. The moral obligation to protect both Earth and alien ecosystems is critical, but it's not just biology that's at risk. Cultural contamination is another significant issue. History on Earth is filled with instances where the contact of technologically disparate cultures led to the erosion or destruction of the less advanced society. If we were to encounter a civilization with vastly different social, moral, or technological frameworks, could our actions result in unintended harm? What responsibility do we bear when interacting with civilizations that may be less equipped to defend themselves against our influence? At the heart of these concerns lies the question of consent. In any interaction, especially with less technologically advanced civilizations, the ability to give informed consent is paramount. How can we as humans ensure that we are not imposing our values or presence on others without their understanding or agreement? This raises questions about whether we have the right to engage in such interactions in the first place. The issue of security and potential hostility also looms large. While we may approach alien life with curiosity and peace, there's always the possibility that contact could result in hostility, either due to misunderstandings or inherent fears. How do we balance the pursuit of knowledge with the safety of our species? Do the potential benefits of contact outweigh the risks? Furthermore, the question of governance is another crucial ethical dilemma. Who decides when and how humanity makes contact with alien civilizations? Who speaks on behalf of Earth? And how do we ensure that such decisions reflect the diversity and values of all nations, cultures, and people on our planet? Lastly, there is the notion of alterity, the ethical recognition and respect for the otherness of alien beings. We must confront the challenge of approaching these encounters without imposing anthropocentric biases. Can we truly understand and value the uniqueness of alien civilizations, or are we doomed to see them through the limited lens of human perspective? Addressing these ethical considerations requires a multidisciplinary approach, one that draws from science, philosophy, sociology, and international law. It demands thoughtful deliberation, careful planning, and a deep respect for the potential consequences of making contact with alien life. This is a responsibility that transcends scientific curiosity and reaches into the realm of moral obligation. The journey into the cosmos is not just about discovering new life. It is about redefining what it means to be human in a universe that may be far more populated than we've ever dared to imagine. As we explore the possibility of extraterrestrial life, we must weigh the potential benefits against the ethical obligations we owe to ourselves, to the planet, and to the beings we may one day encounter. Do you think humanity will ever make contact with life beyond Earth? The future remains uncertain, but the possibilities are nothing short of extraordinary.